Consider a world composed of over 60 million blocks along each horizontal axis, spanning billions of cubic meters, where every single cubic voxel can be individually placed, destroyed, modified, lit, or saved to disk. At first glance, a voxel-based game appears visually simple, almost primitive in its geometry. Yet beneath this blocky surface lies one of the most demanding software engineering challenges in interactive computing. Storing and processing a world of this magnitude using traditional object-oriented game engine architectures would consume hundreds of gigabytes of random access memory within seconds, freezing the system under the weight of billions of heap allocations. Random access memory, or RAM, acts as the computer's high-speed temporary workspace. Inside RAM, software allocates memory in a region called the heap, where dynamic data objects are created during runtime. If an engine creates millions of separate heap objects for every block in a world, system RAM exhausts instantly. The central paradox of voxel software design is how to deliver an effectively infinite, dynamically editable three-dimensional universe while operating strictly within a consumer computer's modest memory footprint and real-time 60 frames per second rendering budget. Today, we will deconstruct the software architecture, data structures, bitwise optimizations, procedural generation pipelines, and multi-threaded systems that make this feat possible. To understand how a voxel engine functions, we must first define what a voxel actually is. A voxel, short for volumetric element, is the three-dimensional equivalent of a flat two-dimensional pixel. Just as a pixel represents a single point of color on a digital screen, a voxel represents a discrete, atomic cube of solid space inside a three-dimensional grid. While a flat screen uses X and Y coordinates to position pixels, a voxel engine uses X, Y, and Z coordinates to position solid cubes in space. Building an engine around voxels requires managing the core trade-offs of rapid prototyping and programming language selection. In computer graphics, three-dimensional terrain is traditionally modeled using polygon meshes or height maps. A polygon mesh models an object by stretching a hollow skin of connected flat triangles over a shape, like a papercraft model. A height map, by contrast, takes a flat two-dimensional grid of elevation numbers and stretches terrain upward like a flexible sheet draped over hills. While height maps are computationally efficient, they suffer from a fundamental topological limitation. They cannot represent overhangs, caves, tunnels, or fully destructible vertical geometry. If you dig a hole straight down into a height map, you simply deform the top surface downward. You do not hollow out a subterranean volume. Voxel engines solve this by representing space as a dense three-dimensional grid of discrete volume elements, or voxels. Each coordinate in space contains explicit spatial data regarding the presence, identity, and state of a block. When building a software engine around voxels, the initial prototyping phase presents a stark choice between immediate rendering speed and flexible world manipulation. Early voxel prototypes in software history drew inspiration from early block-building experiments where world sizes were tiny and statically bounded. However, expanding this concept into an infinite sandbox environment required re-architecting the system from the ground up. In early development iterations, the primary objective was fast iteration and instant visual feedback. Rather than spending months constructing custom engine infrastructure in low-level native code, the initial engine was built using Java. The decision to build a high-performance voxel engine in Java over lower-level alternatives like C++ or assembly is one of the most debated software design choices in game development. To evaluate this decision like a staff engineer, we must examine the technical trade-offs between memory management, compilation targets, and development velocity. C++ provides complete, deterministic control over memory allocation and layout. In C++, an engineer can allocate continuous memory blocks directly on the stack or native heap, control the exact byte packing of data structures down to the individual bit, and execute explicit memory deallocation without runtime overhead. This level of control is ideal for game engines, where predictable frame times are paramount. However, C++ requires manual memory management, platform-specific compilation targets, complex pointer hygiene, and longer build cycles. Java, by contrast, operates on top of the Java Virtual Machine, commonly known as the JVM. The JVM is a software program that acts as an abstract virtual computer inside your system. When Java source code is compiled, it is not converted directly into hardware machine instructions. Instead, it is compiled into intermediate bytecode. Bytecode is a universal set of instructions that the JVM reads and translates into native CPU instructions on any operating system, granting Java its cross-platform portability. The JVM executes this bytecode through a combination of interpretation and just-in-time compilation, known as JIT compilation. Just-in-time compilation means the virtual machine doesn't just slowly interpret bytecode line by line. The JIT compiler monitors running software at runtime, identifies hot loops, code sections like chunk rendering and light propagation executed millions of times per second, and dynamically compiles those bytecode paths into highly optimized, native assembly instructions directly on the fly while the game is running. This grants Java remarkable cross-platform portability. Code written on one operating system can execute identically on another without modifying source code or managing complex platform-specific build toolchains. Furthermore, Java enforces memory safety through automatic garbage collection, eliminating entire classes of memory corruption bugs, double-free errors, and dangling pointers. However, Java's memory safety and runtime abstraction come at a steep architectural cost. In Java, every standard object allocation includes overhead for the object header, which typically consumes 8 to 16 bytes of metadata on a 64-bit virtual machine. If a developer attempts to represent every voxel in a world as an independent object instance containing coordinate integers and state properties, the memory footprint explodes exponentially. A simple block containing 3 coordinate integers and an integer type identifier, which logically requires 16 bytes of raw data, inflates to over 32 or 48 bytes per object due to object header overhead and memory alignment padding. Multiplying this allocation across millions of blocks rapidly exhausts the Java heap, triggering severe performance degradation. This brings us to the single greatest performance bottleneck in early Java voxel engines: the Java garbage collector. The Java garbage collector is an automated housekeeping system inside the virtual machine. Its job is to continuously scan system RAM to locate data objects that are no longer referenced by active code, reclaiming their memory for future allocations. In standard enterprise web applications, brief pauses for garbage collection are often unnoticeable. In a real-time game engine executing at 60 frames per second, the renderer must compute and draw a complete frame every 16.6 milliseconds. If the garbage collector initiates a stop-the-world garbage collection cycle, where all application execution threads are halted while the collector scans and compacts the heap, the rendering pipeline instantly misses its frame target, causing noticeable stutter, frame dropping, and input lag. In early voxel engine iterations, High object allocation rates inside the main game loop created immense memory pressure. Every time a chunk generated new mesh geometry, updated light values, or spawned temporary particle vectors, hundreds of thousands of short-lived objects were allocated on the heap. As these temporary objects died, they fragmented the JVM heap's young generation space, forcing the garbage collector to frequently run promotion sweeps into the old generation heap. These garbage collection sweeps resulted in periodic, jarring frame spikes that degraded the player experience regardless of how powerful the GPU was. These language constraints fundamentally shaped early architectural decisions. Because Java prevented direct pointer arithmetic and custom stack allocated value types in early platform versions, the engine had to be architected around strict memory reusability and primitive array flattening. Instead of allocating thousands of discrete voxel object instances, the engine allocated continuous one-dimensional arrays of primitive integers and bytes. A primitive byte array incurs only a single object header overhead for the entire array, storing millions of primitive byte values contiguously in memory. This eliminated millions of individual heap objects, drastically reducing garbage collection pressure and dramatically improving CPU cache locality. Understanding how data locality impacts CPU performance is essential to understanding voxel engine architecture. Data locality refers to arranging data sequentially in continuous memory blocks. Modern CPUs operate vastly faster than main system RAM. When a CPU core requests data from random access memory, it must wait hundreds of clock cycles for data to travel across the memory bus. To mitigate this latency, CPUs feature multi-level hardware caches. Level 1, Level 2, and Level 3 caches located directly on the processor die, which act as tiny, hyperfast memory pools categorized by speed and capacity. When the CPU reads a byte from main memory, it doesn't read just that single byte. It fetches an entire continuous line of memory, typically 64 bytes, into the CPU cache. If the engine iterates through a contiguous primitive array stored sequentially in memory, adjacent block data is prefetched into the CPU cache ahead of execution. This yields a high cache hit ratio, allowing the processor to execute spatial loops at peak hardware efficiency. Conversely, if the engine traverses an array of object references scattered randomly across the heap, every block lookup results in a cache miss, stalling the CPU core as it waits for main memory. To fully understand how JVM execution impacts real-time performance, we must examine the internal tiering of Java just-in-time compilation, object layout semantics, and memory alignment rules. When Java application code launches, the virtual machine initially executes bytecode using a fast interpreter. As execution loops run repeatedly, such as chunk render mesh generation or BFS light propagation, the JVM profiling engine monitors loop execution counts. When a method or loop execution count crosses a predefined hotspot threshold, the JVM schedules the method for JIT compilation. In modern virtual machines, JIT compilation is tiered into two distinct compiler engines: the C1 compiler, known as the client compiler, and the C2 compiler, known as the server compiler. The C1 compiler executes rapid compilation passes, converting bytecode into native machine instructions with minimal compilation delay. It performs basic optimizations like method inlining and dead code elimination, delivering an immediate performance boost for game startup loops. Meanwhile, the C2 server compiler executes deep, complex optimization passes in the background. The C2 compiler analyzes execution profiling data to apply aggressive optimizations, including loop unrolling, SIMD vectorization, and escape analysis. Escape analysis evaluates whether an object allocated inside a method escapes the method's stack frame boundary. If an object, such as a temporary vector coordinate or light update task, never escapes local method scope, the C2 compiler applies scalar replacement. Scalar replacement completely eliminates heap allocation for that object. Instead of allocating memory on the heap and instantiating an object header, the C2 compiler decomposes the object into its scalar primitive fields and maps those primitives directly to CPU hardware registers or local thread stack frames. Scalar replacement eliminates heap allocation overhead and garbage collection pressure for temporary calculations, allowing hot loops to run at near-native C++ speeds. However, scalar replacement has strict architectural limits. If an object is stored inside an array, passed across thread boundaries, or assigned to a field on a heap object, escape analysis fails. The JVM is forced to allocate the object on the managed heap, triggering object header allocation and memory alignment padding. To analyze object layout like a systems performance engineer, consider how a 64-bit JVM formats memory. Every object allocated on a 64-bit Java heap contains a multi-word object header comprising two primary fields, the mark word and the class word. The mark word consumes 8 bytes on a 64-bit system, storing runtime metadata including object hash codes, GC generational age bits, biased locking state flags, and thread synchronization lock pointers. The class word points to the native C++ class metadata structure defining the object's type and method tables. On a pure 64-bit virtual machine, the class word consumes another 8 bytes, resulting in a 16-byte header overhead before a single byte of instance data is stored. To reduce header overhead across large heaps, JVM software engineers invented compressed ordinary object pointers, known as compressed OOPs. Compressed OOPs exploit memory alignment rules to compress 64-bit object reference pointers down to 32 bits. In Java, all objects allocated on the heap are aligned to 8-byte memory boundaries. Because every object address is a multiple of 8, the lowest 3 bits of any valid object address pointer are always 0. Compressed OOPs discard these 3 0 bits, storing only the upper 35 bits of the memory address shifted to the right by 3. When a thread dereferences a compressed pointer, the CPU executes a bitwise left shift by 3 positions, pointer F3, to reconstruct the full 64-bit native memory address. Compressing object pointers down to 32 bits shrinks heap reference array sizes by 50%, drastically improving CPU cache line density and extending effective heap capacity up to 32 gigabytes of RAM. Beyond object headers and pointer compression, managing JVM performance requires understanding generational garbage collection memory topologies. The JVM heap is divided logically into 2 primary spaces, the young generation and the old generation. The young generation is further partitioned into the Eden space and 2 survivor spaces, designated Survivor 0 and Survivor 1. New objects allocated inside the main game loop, such as temporary particle vectors or NBT parsing tags, are instantiated inside the Eden space. Because most temporary objects die shortly after allocation, the JVM uses a fast copying garbage collector algorithm for young generation sweeps, known as minor GC. When the Eden space fills up, a minor GC sweep halts application threads briefly, identifies surviving objects, copies them into Survivor 0, and clears the entire Eden space instantly. Objects that survive multiple minor GC sweeps age incrementally. Once their generational age crosses a promotion threshold, they are promoted into the old generation heap space. However, when long-lived objects such as loaded chunk arrays, entity maps, and region file buffers accumulate in the old generation, they trigger major GC or full GC sweeps. Unlike minor GC, an old generation sweep requires scanning and compacting multi-gigabyte memory regions, resulting in long, jarring stop-the-world pauses that stall the game loop. To minimize old generation sweep pauses, high-performance engines use object pooling and primitive array flattening. By allocating persistent primitive byte arrays at engine startup and recycling them across chunk generations, the engine bypasses Eden allocation entirely, eliminating minor GC sweeps and ensuring that heap memory remains completely stable over multi-hour exploration sessions. Now that we have established the underlying memory constraints and language environment, we can analyze the core synchronization engine, the main game loop. A game engine relies on a continuous loop that processes user input, updates world state logic, simulates physics, and renders visual frames to the screen. In simple game architectures, the game loop runs synchronously on a single thread. It pulls keyboard and mouse inputs, calculates object positions based on elapsed time, and commands the graphics API to render the frame. However, relying on a variable frame rate for game logic simulation introduces severe instability. If game logic updates are tied directly to rendering frame rates, a player running the game at 120 frames per second would experience world physics executing twice as fast as a player running at 60 frames per second. To prevent this, professional game engines decouple rendering frame rates from logical simulation rates. Voxel world engines standardize their internal world simulation around a fixed tick rate of 20 ticks per second, or 20 Hz. A tick is a single simulation step or heartbeat of the game world loop. Operating at 20 Hz means the world simulation ticks 20 times per second, executing a complete update cycle every 50 milliseconds regardless of how fast the graphics card renders frames. During each 50 millisecond tick interval, the engine executes a deterministic sequence of world updates. It increments the world time counter, processes entity movement and collision detection, updates environmental physics like flowing liquids and falling gravity blocks, recalculates redstone circuit state changes, runs random crop growth ticks across loaded chunks, and processes entity artificial intelligence logic. If a single tick completes in 10 milliseconds, the engine sleeps for the remaining 40 milliseconds to maintain a steady 20 Hz cadence. However, real-world hardware environment variations mean a server or client thread may occasionally experience computational overload, causing a tick to take longer than 50 milliseconds. If a heavy explosion causes a tick to take 80 milliseconds, the engine enters a tick drift state. To recover from tick drift, the engine implements catch-up logic. On the subsequent tick cycle, the engine detects that it has fallen behind scheduled target time and immediately executes back-to-back tick updates without sleeping, accelerating world simulation until the internal tick clock realigns with real-world elapsed time. If server load is so extreme that tick execution repeatedly exceeds 50 milliseconds, the engine experiences server lag, causing world simulation to slow down relative to real-time player actions. A pivotal architectural transformation in voxel engine history was the client-server unification overhaul. In early engine iterations, single-player mode and multiplayer mode operated on entirely different code-base foundations. Single-player mode ran a single monolithic game loop where input, world simulation, and rendering were tightly coupled. Multiplayer mode, by contrast, ran a dedicated background server application that managed world state and communicated with connected client applications over TCP and UDP network sockets, maintaining two distinct code paths for single-player and multiplayer features created severe engineering overhead. Every new feature, block type, or entity physics logic had to be implemented twice, once for the single-player engine and once for the multiplayer network protocol. To eliminate this redundancy, the architecture was completely unified by integrating an internal embedded server instance directly into the single-player client application. Under this unified architecture, when a user launches a single-player world, the application spins up a local background server thread running on an internal loopback network loop. The client interface code acts as a local network client, connecting to the internal server over an in-memory loopback pipeline. All world simulation, chunk generation, entity physics, inventory management, and block placement logic are owned exclusively by the internal server thread. The client thread is responsible strictly for rendering the world, processing user input, playing audio, and displaying user interface screens. This client-server unification achieved remarkable engineering advantages. First, it completely eliminated code duplication. Single-player and multiplayer modes use identical world simulation logic, network packet serialization structures, and entity update handlers. Second, it isolated world logic from client rendering bugs. If the rendering thread experiences a visual lag spike due to complex shader compilation or window resizing, the internal server thread continues ticking the world at 20 Hz without interruption. Third, it allowed seamless single-player world hosting, enabling a single-player game to open its local world to local area network connections instantly by listening on a network port. However, unifying client and internal server architectures introduced complex multithreading and state synchronization challenges. Because the internal server and client render threads run concurrently, they must share state without introducing race conditions, thread deadlocks, or spatial tearing. For example, if the server thread updates an entity's position coordinate in memory while the client rendering thread is simultaneously reading that coordinate to compute a vertex matrix for drawing, the renderer could read a partially updated vector, resulting in visual jitter or crashes. To solve this, the engine enforces strict thread separation rules and thread-safe messaging channels. The server thread maintains the authoritative state of the world. It processes client inputs, such as player movement vectors and block break commands, and broadcasts state update packets back to the client thread. The client thread maintains a separate, client-side mirror of the world state specifically formatted for rendering. To ensure smooth visual motion between coarse 20 Hz server ticks, drawing entity positions directly from raw server tick coordinates would result in visibly jerky motion. The client renderer solves this by implementing linear interpolation using partial ticks. The renderer stores both the previous tick position and the current tick position for every visible entity, calculating a fractional tick offset representing how far the current frame time is between ticks. It then applies linear interpolation between the two positions, creating fluid visual motion at 60 or 120 frames per second without altering authoritative server coordinates. Concurrency extends far beyond simple position interpolation. Modern voxel engines utilize multi-threaded task graphs to offload expensive asynchronous background operations away from the main tick and render threads. Operations such as procedural terrain noise calculations, region file disk reads and writes, lighting propagation updates, and vertex buffer generation are dispatched to dedicated worker thread pools. By decoupling these asynchronous tasks from the primary simulation loops, the engine ensures that world generation and disk persistence occur seamlessly without stuttering the user's rendering or movement experience. To construct a world of infinite cubic volumes, we must transition from temporal synchronization to spatial mathematics. In standard three-dimensional graphics, digital assets are modeled using boundary representations or polygon meshes. A mesh defines an object by its outer shell, using a hollow collection of vertices, edges, and triangular faces. While polygon meshes excel at representing complex, smooth surface curves for characters and static vehicles, they are fundamentally ill-suited for real-time volumetric destruction. If a player attempts to blow a hole in a polygon mesh model, the engine must perform complex online mesh Boolean operations. It must slice intersecting triangles, retriangulate open boundaries, generate new interior surface UV texture coordinates, and update spatial acceleration trees like bounding volume hierarchies. Executing thousands of dynamic mesh Boolean operations per second across a massive world is computationally prohibitive and prone to topological geometry errors like non-manifold edges. Voxel grids solve this problem by abandoning surface-only boundary representations in favor of volumetric spatial discretization. Space is treated not as a hollow vacuum populated by surface skins, but as an explicit, dense three-dimensional grid of uniform atomic cubes. In a voxel grid, editing the world does not require recalculating complex geometric topologies. Modifying a block simply requires mutating a discrete value at a specific coordinate in a spatial data structure. If a player mines a stone block, the engine replaces the block identifier at those coordinates with an air identifier. The volumetric structure remains pristine. Only the categorical state of that specific spatial index changes. However, storing a dense volumetric grid poses severe memory efficiency challenges. Consider a single spatial cube measuring 16 blocks along each axis. This small volume contains 4,096 individual voxel coordinates. If each voxel were represented as a naive object structure containing 64-bit integer coordinates, string names, light levels, and orientation flags, a single chunk of world space would consume several megabytes of heap memory. Extrapolating this to a rendered view distance of 32 chunks in every direction, which encompasses over 80,000 loaded chunks, would require hundreds of gigabytes of RAM just to store raw block data. To resolve this spatial memory paradox, voxel software architects implement primitive flattening, bit packing, and dynamic palette compression. Rather than using multidimensional object arrays, block data is flattened into contiguous one-dimensional primitive byte arrays. In early engine iterations, a block's identity was represented by an 8-bit byte, providing 256 unique block type identifiers, paired with a 4-bit metadata nibble array storing additional state flags such as stair orientation or furnace ignition status. To store 4-bit nibbles efficiently without wasting half of an 8-bit byte per block, the engine packed two adjacent 4-bit nibbles into a single byte using bitwise shifting and bit masking operations. As voxel worlds evolved to support thousands of distinct block types, properties, and states, static 12-bit representation proved insufficient. Software architects responded by introducing dynamic subchunk palette compression. Under palette compression, space is divided vertically into 16 by 16 by 16 block volumes called subchunks. Palette compression operates like an artist's paint palette. Instead of identifying every block using a massive global number that consumes significant memory bits, each subchunk maintains its own local palette array. The local palette acts as a short lookup dictionary mapping small local integer indices to global block state definitions. To visualize palette compression, imagine a subchunk located deep underground, comprised entirely of stone and dirt, with air filling a small cave passage. Although the overall engine supports thousands of unique block states, this specific subchunk contains only 3 distinct block types: stone, dirt, and air. Rather than allocating 16 bits per block to store global state identifiers, the engine constructs a local palette containing only 3 entries. Index 0 represents air, Index 1 represents stone, and Index 2 represents dirt. Because 3 unique entries require only 2 bits of storage per index, the engine compresses the block data array so that every voxel index consumes exactly 2 bits of memory. The engine packs these 2-bit indices sequentially into a continuous array of 64-bit long integer primitives. A single 64-bit long word can store 32 2-bit block indices packed tightly side by side. If a player places a redstone wire or a chest in that subchunk, introducing a 4th and 5th unique block type to the local palette, the palette size grows to 5 entries. 5 entries require 3 bits per index. The engine dynamically reallocates the underlying data array, shifting the bit width per entry from 2 bits to 3 bits, and repacks the block data. Palette compression dramatically shrinks the memory footprint of uniform terrain, allowing vast regions of deep stone or open sky to consume virtually 0 memory while maintaining total flexibility for complex build areas. Accessing block data inside these packed primitive arrays requires fast spatial indexing math. In a 3-dimensional grid, a block is identified by local coordinates x, y, and z, ranging from 0 to 15 within a subchunk volume. To convert these 3 discrete spatial coordinates into a single linear offset within a 1-dimensional memory array, the engine applies spatial flattening math. By organizing memory in YZX column order, the linear array index is calculated using the formula local y plus local z multiplied by 16 plus local x multiplied by 256. In performance-critical hot paths, hardware CPU execution can be further accelerated by replacing arithmetic multiplication and addition with bitwise shift and bitwise OR operations. Bitwise operators work directly on the raw binary ones and zeros of computer data at the hardware level. An arithmetic right shift slides binary digits to the right, which divides an integer by powers of 2 in a single CPU instruction cycle, while a bitwise and mask filters out unwanted binary digits, extracting remainders instantly without using slow arithmetic division or modulo instructions. Because 16 is 2 to the 4th power and 256 is 2 to the 8th power, multiplying coordinate values by these factors is binary equivalent to shifting their bit representations to the left. The linear array offset is computed instantly by taking local y, bitwise ORING local z shifted left by 4 bits, and bitwise ORING local x shifted left by 8 bits. Bitwise operators execute in a single CPU instruction cycle, bypassing arithmetic multiplication pipelines and enabling lightning-fast voxel lookups during render mesh generation and physics collision testing. Spatial representation extends beyond integer block coordinates to continuous floating-point vector mathematics. Entities, cameras, light vectors, and physics particle systems exist in continuous world space defined by double-precision floating-point numbers. Translating between continuous double precision entity coordinates and discrete integer block coordinates is a frequent, critical operation. Converting a continuous coordinate to a block coordinate requires floored integer casting rather than standard truncation. Standard floating point truncation rounds toward 0. Positive 1.5 truncates to positive 1, but negative 1.5 truncates to negative 1. This creates an asymmetric coordinate distortion at the world origin where negative coordinates shift by a block offset. Implementing custom bitwise math flooring ensures consistent block boundary alignment across all coordinate quadrants. Furthermore, managing floating point math at massive coordinate distances introduces the fundamental problem of floating point precision loss. In IEEE 754 double precision floating point arithmetic, numbers are represented using a sign bit, an exponent, and a mantissa. As coordinate values grow larger, more bits of the mantissa are consumed to represent the whole integer portion of the coordinate, leaving fewer bits to represent the fractional decimal precision. At extreme spatial distances millions of blocks away from the world origin, the fractional distance between representable floating point values increases dramatically. This historic mathematical boundary condition caused spatial rounding jitter, physics instability, and visual vertex tearing known as coordinate drift. Modern voxel architectures solve this by utilizing localized relative coordinate frames, shifting rendering matrix origins relative to the camera position on every frame so GPU calculations always execute within high-precision near-zero origin space. Building upon floating point vector mathematics and spatial grid indexing, the engine implements two core spatial traversal systems: the voxel physics collision engine and the 3D digital differential analyzer raycasting engine. The voxel physics collision engine governs how entities, such as players, animals, projectiles, and falling blocks, interact physically with solid voxel geometry. Unlike continuous physics engines that compute complex mesh-to-mesh rigid body dynamics, voxel collision testing exploits grid spatial partitioning for extreme performance. Entities are encapsulated within axis-aligned bounding boxes, known as AABBs. An axis-aligned bounding box, or AABB, is an invisible six-sided rectangular box enclosing an entity defined by two 3D vector points, minimum XYZ coordinates and maximum XYZ coordinates. The box is termed axis-aligned because its six faces are constrained parallel to the world's primary Cartesian axes: north-south, east-west, and up-down, completely eliminating rotational matrix transformations and simplifying collision overlap math. When an entity moves with a velocity vector, the physics engine must test whether the entity's path intersects solid blocks. If the engine executed continuous collision sweeps across the entire world, collision testing would slow down tick execution. Instead, the engine constructs a candidate block search space. To calculate candidate blocks, the physics engine expands the entity's current AABB to encompass its projected target destination AABB, creating a swept bounding box. The engine converts the minimum and maximum floating point bounds of the swept AABB into integer block coordinates using floored casting, extracting a small, discrete 3D spatial search box containing only blocks that could potentially intersect the entity's trajectory. For every solid block inside the search box, the engine retrieves its individual block collision AABB. A standard full stone block has a collision box spanning 0.0 to 1.0 along all three axes. Non-standard blocks, such as stairs, slabs, fences, or open trapdoors, have custom subblock collision boxes. to prevent an entity from clipping through walls or falling through floors when moving at high speeds. A failure mode known as tunneling, the physics engine resolves collisions along each Cartesian axis independently. The algorithm evaluates movement along the y-axis first. It shifts the entities ABB by the y-velocity component, tests for ABB overlap against candidate block boxes, and if an intersection occurs, clips the entity's y-velocity to line up exactly flush against the block surface. Once y-axis movement is resolved and applied, the engine repeats the exact same overlap test independently along the x-axis, and finally along the z-axis. Resolving Cartesian axes independently prevents diagonal corner clipping errors, allows players to smoothly slide along stone walls without catching on block seams, and provides rock-solid floor support for gravity calculations. Complementing bounding box collision physics is the voxel raycasting engine, which handles line-of-sight testing, block targeting, player mining reach, and projectile trajectory prediction. When a player crosshair points at the landscape and clicks to mine or place a block, the engine must determine exactly which voxel face the player is targeting in 3D space. Executing naive ray casting by sampling points at tiny fixed distance intervals along a ray vector is computationally inefficient and prone to missing thin block edges. Instead, voxel engines implement the fast Aminatides and Wu 3D digital differential analyzer algorithm, known as 3D DDA. Digital differential analysis raycasting traces a view ray through a 3D grid room by room, calculating the exact distance to the next voxel boundary plane along each axis rather than stepping forward in small blind increments. The 3D DDA raycasting algorithm treats the player's view vector as a parametric ray starting at origin point O with directional unit vector d. Rather than stepping through space by small floating point increments, 3D DDA calculates the exact distance required for the ray to cross from its current voxel into the adjacent neighbor voxel along each spatial axis. To visualize 3D DDA, imagine a ray traveling diagonally through a 3D grid of cubic rooms. The algorithm tracks 3 key variables per axis: step x, step y, and step z, which record whether the ray is moving positively or negatively along each coordinate axis. Tmax x, Tmax y, and Tmax z, which store the parametric ray distance to the next immediate voxel boundary plane along each axis, and T-delta x, T-delta y, and T-delta z, which record the constant parametric ray distance required to traverse the full width of a single cubic voxel along each axis. During execution, the 3D DDA loop compares Tmax values across the 3 axes. If Tmax x is the smallest, the ray will cross an x-axis voxel boundary plane first. The algorithm increments the current voxel x coordinate by step x, updates Tmax x by adding T-delta x, and records the targeted voxel face as east or west. If Tmax y is smallest, the ray steps into the next y voxel, updating Tmax y and recording the face as top or bottom. The 3D DDA algorithm executes in a single loop iteration per voxel boundary traversed, performing simple floating point comparisons without trigonometric calculations or square roots. The loop terminates the instant it encounters a non-air solid voxel or exceeds maximum player reach distance, returning both the targeted voxel coordinates and the exact hit face vector allows the engine to instantly highlight targeted blocks and determine valid block placement surfaces. Now that we understand spatial representation and vector math in cubic grids, we can examine how these vast environments are procedurally generated from scratch using mathematical noise functions. The core requirement of procedural world generation is infinite determinism. A player should be able to input an arbitrary string or integer seed, such as a word or random 64-bit number, and the engine must generate a fully formed, continuous universe spanning mountain ranges, river networks, caves, and biomes. Furthermore, this generation must be completely deterministic. Entering the exact same seed on different computers running different operating systems must produce the exact same block layout down to the individual voxel. Determinism is achieved through pseudorandom number generators, or PRNGs, combined with seed hashing algorithms. A pseudo-random number generator, or PRNG, is a mathematical algorithm that accepts an initial input number, known as a seed, and calculates a sequence of numbers that appears random, but is entirely reproducible. Passing the exact same seed into a PRNG on different computers produces the exact same numerical sequence, enabling infinite deterministic world generation. Standard algorithms like linear congruential generators or Zorshift algorithms process 64-bit integer state variables using bitwise shifts, multiplications, and XOR masks. To ensure that chunk generation at coordinate x and z is independent of the order in which chunks are loaded, the engine does not rely on a single sequential random stream. Instead, it computes a unique positional seed for each chunk by combining the global world seed with the chunk's spatial coordinates using bit-mixing hash functions. This guarantees that a chunk located at spatial coordinate x500, z1000 generates identically whether the player approaches it from the north, south, or teleports directly to it. However, raw pseudorandom numbers alone cannot generate coherent terrain. If you assign a completely random height value to every coordinate column, the world becomes a chaotic, unplayable static noise field where adjacent blocks have zero spatial correlation. To generate recognizable landscapes with smooth hills, valleys, and continuous cliff faces, the engine relies on coherent gradient noise algorithms, primarily Perlin noise and Simplex noise. Gradient noise algorithms transform random seeds into smooth, continuous mathematical waves across space, generating realistic rolling landscapes rather than chaotic static. Perlin noise transforms random seeds into smooth, continuous spatial density fields. Visualize a two-dimensional grid drawn over a plane. At every integer grid intersection point, the algorithm assigns a pseudorandom unit vector called a gradient vector, derived deterministically from the world seed. When calculating the noise value for any arbitrary continuous point on the plane, the algorithm determines which grid cell the point falls inside. It calculates displacement vectors from the 4 surrounding grid corners to the point, computes the mathematical dot product between each corner's gradient vector and its corresponding displacement vector, and smoothly interpolates those 4 dot product values across the cell area. To make the spatial transitions smooth and visually natural, Perlin noise uses a quintic S-curve interpolation function. The quintic curve ensures that both the first and second derivatives of the noise function are 0 at grid boundaries, eliminating sharp derivative creases and creating soft, rolling topographical contours. Despite its brilliance, standard Perlin noise suffers from computational scale limits and directional grid alignment artifacts when expanded into 3-dimensional volumes. Calculating 3D Perlin noise requires evaluating 8-unit gradient vectors and performing 7 cubic interpolation steps per spatial sample. As generation algorithms scale to evaluate dense 3D volumetric noise fields for overhangs and cave networks, 3D Perlin noise becomes a severe CPU bottleneck. Furthermore, because Perlin noise evaluates hypercubic grid cells, terrain features can display subtle grid-aligned cardinal bias. To overcome these limits, modern engines utilize Simplex noise. Simplex noise replaces hypercubic grid cells with n-dimensional triangular simplexes. In 2 dimensions, a simplex is an equilateral triangle. In 3 dimensions, it is a regular tetrahedron. Instead of evaluating 8 grid corners as in a 3D cubic Perlin grid, 3D simplex noise evaluates only 4 corners of the surrounding tetrahedron. This reduces the mathematical complexity from O(2 to the power of n to O(n squared) for n spatial dimensions, significantly accelerating 3D volumetric sampling rates while completely eliminating square grid directional artifacts. While a single layer of Perlin or simplex noise creates smooth waves, real-world terrain possesses multi-scale complexity. Massive mountain ranges feature sharp ridge lines, medium hills, and subtle surface erosion details. To replicate this multi-scale complexity, procedural world engines implement octave layering. Octaves are independent layers of a noise function stacked on top of each other at progressively higher frequencies and lower amplitudes. Low-frequency base octaves establish massive continent shapes, while higher-frequency octaves add medium hills, cliff ledges, and fine surface gravel. Octave layering sums multiple independent iterations of a noise function, called octaves, at progressively higher frequencies and lower amplitudes. Visualize sound waves. A deep fundamental bass frequency establishes the overall shape of a tune, while higher harmonic overtones add rich timbre and acoustic texture. In procedural terrain generation, the first octave, the bass octave, uses a low spatial frequency and a high amplitude. This bass octave carves out macroscale topography, defining where massive continents rise and deep ocean basins sink. The second octave doubles the spatial frequency and halves the amplitude. It is added directly to the bass octave, adding medium-sized hills and river valleys to the continental contours. The third octave quadruples the spatial frequency and quarters the amplitude, layering small boulders, surface bumps, and cliff ledge variations over the terrain. The controls governing octave summation are lacunarity, which defines the frequency multiplier between octaves, typically set to 2.0, and persistence, which defines the amplitude decay factor, typically set to 0.5. By adjusting lacunarity, persistence, and total octave counts, terrain generators produce vastly different landscape styles. High persistence creates jagged, chaotic alpine peaks, while low persistence creates gentle, flat plains. Furthermore, software architects utilize domain warping to generate breathtaking overhangs, floating islands, and organic serpentine cave structures. Domain warping feeds the continuous floating point output of one noise function directly into the coordinate input parameters of another noise function. By warping coordinate space before sampling final density fields, straight noise ridges twist into organic arches, hollowed-out stone bluffs, and winding underground caverns. Topography alone, however, does not make a complete world. Landscapes must be populated with realistic ecological biomes like deserts, snowy tundras, rainforests, and savannas. Early procedural engines assigned biomes using simple two-dimensional maps based on distance from origin or basic height thresholds. Modern voxel engines utilize multidimensional parametric climate matrices. A parametric climate matrix samples multiple continuous 3D noise channels representing physical environment factors, such as temperature, humidity, erosion, and continentalness, projecting these values into a multidimensional climate space to select matching biomes naturally. During world generation, for every chunk column, the generator samples these continuous noise values, yielding a multidimensional point vector in climate parameter space. The engine then projects this point vector into a precomputed parametric lookup dictionary containing defined biome vectors. By calculating the Euclidean distance between the sampled climate point and nearby biome target vectors in multidimensional space, the engine selects the closest matching biome definition. This parametric matrix approach produces breathtakingly natural ecological transitions. Hot, dry climate zones smoothly spawn deserts adjacent to arid savannas, while cold, humid zones naturally form snowy taiga forests, eliminating artificial biome border collisions. Beyond continuous terrain elevation and climate biomes, a complete procedurally generated universe requires populating landscapes with complex, multi-block structures, such as villages, strongholds, ocean monuments, nether fortresses, mineshafts, and ancient subterranean cities. Placing multi-block structures across an infinite voxel grid introduces monumental spatial algorithms. How to assemble complex, non-repeating architectural structures deterministically without causing spatial overlaps, broken doorways, or boundary corruption across chunk seams. Voxel software architects solve this using the jigsaw assembly algorithm paired with NBT structure template pools. Rather than hard-coding static structure layouts in code, structures are broken down into modular architectural components saved as binary NBT structure templates, such as individual house rooms, street corridors, towers, wall sections, and staircase junctions. Each NBT structure template contains specialized spatial metadata blocks called jigsaw blocks. A jigsaw block acts as a multi-directional connection socket, defining a target attachment pool name, a local attachment name, and a spatial orientation vector. When the procedural engine determines that a village should generate at a specific chunk coordinate, it retrieves the root village structure template, typically a central town square, from the village template pool. The engine places the root template into the world, identifies all open jigsaw connection sockets on the root piece, and registers them in a pending assembly queue. During assembly execution, the generator pops a pending jigsaw socket from the queue. It queries the target template pool specified by the socket, selects a compatible matching structure piece using deterministic seed random weighting, and rotates the candidate piece in 3D space to align its connection socket flush with the parent socket. Before confirming piece placement, the structure generator performs axis-aligned bounding box intersection checks. The candidate piece's bounding box is tested against all previously placed structure pieces in the village assembly. If an intersection is detected, such as a street corridor attempting to clip through an existing house wall, the engine rejects the piece, discards the candidate, and attempts to select an alternative piece or caps the open socket with a solid wall template. Assembly continues recursively through child jigsaw sockets until maximum assembly depth is reached or all open sockets are capped. Using jigsaw assembly algorithms allows procedural engines to construct sprawling, organic villages, subterranean cities, and multi-level dungeons with thousands of unique room layouts while guaranteeing structural integrity. Following macrostructure assembly, the terrain generator executes the feature decorator pipeline. Feature decorators populate chunks with small-scale natural elements, or veins, trees, giant mushrooms, lava springs, flower patches, and mob spawners. Decorators execute in a strict deterministic sequence using specialized spatial height map algorithms. To place trees efficiently without scanning every vertical block in a chunk, the generator queries the chunk's world surface height map. The world surface height map is a flattened 16 by 16 byte array recording the highest non-air block coordinate for every XZ column. The tree decorator selects random XZ coordinates within the chunk, checks the height map for surface elevation, and evaluates soil block type and overhead light levels. If environmental criteria are satisfied, the decorator places with log trunks and generates leaf canopy geometries based on procedural L-system branching rules or static NBT foliage templates. Furthermore, underground or vein decoration, such as coal, iron, gold, and diamond, is governed by 3D ellipsoidal spline sampling. Rather than placing square blocks of ore, the engine constructs a 3D parametric ellipsoid vector, orienting the ellipsoid along a pseudo-random 3D direction vector derived from the chunk seed. The engine steps along the ellipsoid line, replacing stone blocks with or voxels according to depth-based rarity distributions. Layering jigsaw assemblies and featured decorators over procedural noise terrain creates a rich, endlessly fascinating universe populated by natural flora, mineral wealth, and ancient architectural ruins. Now that we have deconstructed procedural generation and parametric climate modeling, we must explore how the engine partitions, loads, renders, and lights this procedurally generated world in real time. The key spatial partitioning abstraction in voxel engines is the chunk system. A computer cannot load or process an infinite world simultaneously. Doing so would saturate system memory and crash the application. To solve this, spatial software architects divide the infinite world into discrete, manageable spatial volumes called chunks. A chunk is a continuous vertical column measuring 16 blocks along the horizontal x-axis, 16 blocks along the horizontal z-axis, and extending vertically across the entire world height limit. Dividing space into uniform 16 by 16 vertical volumes creates a spatial partitioning grid where world state is dynamically loaded and unloaded based on player proximity. As a player moves through the world, the engine maintains a square or circular rendering window around the player's coordinate, loading active chunks within the defined view distance and unloading distant chunks behind them. To execute spatial lookups at maximum performance, the engine converts global world block coordinates into chunk coordinates and local block offsets using low-level bitwise arithmetic. In a standard base 10 number system, dividing a number by 10 shifts its decimal digits to the right. In a binary computer system, dividing an integer by 16, which is 2 to the 4th power, is achieved instantly by executing an arithmetic right shift by 4 bits. Visualize a global block coordinate of x67. In binary representation, 67 is 0, 1, 0, 0, 0, 0, 11. Shifting these bits to the right by 4 positions removes the 4 lowest bits, leaving 0, 1, 0, 0, which equals 4 in decimal. Thus, block x67 resides inside chunk x4. To find the block's local offset within that specific chunk, the engine needs the remainder of 67 divided by 16. Rather than executing an expensive modulo division instruction, the engine performs a bitwise an operation with 15, which in binary is 4 ones. The bitwise and masks out everything except the lowest 4 bits, returning 3. In a single clock cycle, the engine determines that global block x67 translates to local offset 3 inside chunk x4. This bitwise coordinate conversion happens billions of times per second across chunk loading, physics testing, light updates, and render mesh construction. By structuring chunk dimensions around powers of 2, specifically 16, the software architect bypasses CPU arithmetic pipelines entirely executing spatial indexing at the hardware bit level. The life cycle of a chunk is managed by a sophisticated asynchronous state machine. When a player moves toward an ungenerated region of the world, the chunk enters the generation queue. Generating a chunk is not an instant atomic operation. It progresses through a strict multi-stage pipeline designed to prevent spatial boundary dependencies and thread race conditions. In the first stage, the noise generation stage, worker threads sample multidimensional noise fields to build the raw volumetric stone and water layout. In the second stage, the surface placement stage, the engine layers grass, dirt, and sand over the raw stone density map based on biome parameters. In the third stage, the structure carving stage, the generator carves out cave tunnels and underground mine shafts. In the fourth stage, the decoration and structure placement stage, the engine places trees, flora, villages, and complex dungeons. However, placing multi-chunk structures like villages or large trees introduces a critical boundary dependency. A tree growing near the edge of chunk A might extend its leaves across the spatial border into chunk B. If chunk B has not yet undergone initial noise terrain generation, placing leaf blocks into chunk B would cause spatial corruption or deadlocks. To resolve this, the engine enforces a strict multi-stage generation buffer, ensuring that adjacent chunks are always at least one step ahead in terrain generation before structure decoration is allowed to write across spatial borders. Once a chunk completes structure decoration, it enters the light propagation stage, where initial sky and block lighting values are calculated. Finally, the chunk reaches the active state where it is transferred to main system memory, registered with the rendering pipeline, and ticked by the world simulation loop. When the player moves far away, the chunk enters the dirty state review. If the chunk was modified by block placement or entity actions, it is serialized asynchronously to disk before being safely evicted from heap memory to free resources for incoming chunks. Once chunks are loaded into memory, the engine faces a monumental rendering challenge, drawing millions of three-dimensional cubes at real-time frame rates. In computer graphics, rendering performance is dictated largely by the number of draw calls sent from the CPU to the graphics processing unit, or GPU. A draw call is a command sent over the PCI Express bus instructing the GPU to render a collection of geometry. If an engine sends an individual draw call for every single block in a loaded view distance, which can encompass millions of blocks, the CPU overhead of issuing draw call commands degrades frame rates to single digits, creating a severe CPU-bound bottleneck. To overcome this, voxel engines implement batch rendering using OpenGL vertex buffer objects, or VBOs, and vertex array objects, or VAOs. A vertex buffer object, or VBO, is a consolidated memory buffer stored directly on the graphics card holding thousands of block vertices, allowing the CPU to issue a single draw call for an entire subchunk volume. Instead of issuing individual draw calls per block, the engine bakes an entire 16 by 16 by 16 subchunk volume into a single, continuous geometric mesh. The CPU iterates through the subchunks block arrays, constructs a consolidated array of vertex positions, normal vectors, and UV texture coordinates for all visible block faces, and uploads this raw binary mesh data directly to GPU VRAM into a single VBO. The renderer then issues a single draw call per subchunk, allowing the GPU's massively parallel rasterization pipeline to render thousands of blocks in a fraction of a millisecond. Batching geometry into VBO subchunk meshes introduces a major GPU texture mapping challenge. How to render hundreds of unique block textures, such as grass, dirt, stone, wood, and water, within a single batch draw call without binding a new texture for every block face. In graphics APIs like OpenGL or Vulkan, changing the active bound texture object forces a pipeline state change. If an engine issues state changes for every block type, GPU draw call batching is destroyed. To preserve draw call batching across diverse block types, the graphics engine implements texture atlas stitching. A texture atlas is a single, large, high-resolution texture sheet, such as a 512 by 512 or 1024 by 1024 pixel image that stitches individual 16 by 16 block textures together into a unified grid atlas. When the CPU builds a subchunk VBO mesh, it assigns normalized UV texture coordinates to each vertex based on the block's position within the global texture atlas. UV coordinates range from 0.0 to 1.1 across the horizontal U and vertical V axis of the atlas. To map a stone texture located at column 2, row 4 of the atlas, the vertex generator calculates the exact fractional UV bounding box spanning that texture cell. However, rendering a stitched texture atlas introduces visual sampling artifacts known as texture bleed. When distant block faces are rendered at shallow viewing angles, the GPU's bilinear texture filtering sampler interpolates texels along the outer boundary of a block's UV coordinate frame. If UV coordinates lie exactly on the cell boundary, bilinear filtering samples adjacent texels from neighboring block textures in the atlas, causing faint, ugly colored lines to appear around block edges. Graphics software architects eliminate texture bleed through UV padding and half-texel offset corrections. When generating vertex UV data, the engine applies a minute inward offset to the bounding box coordinates, shrinking the sampling rectangle by half a texel width. Half-texel offset padding guarantees that bilinear filtering samplers remain strictly within the interior pixels of the target block texture, eliminating border bleed artifacts entirely. Beyond texture atlas stitching, rendering distant voxel terrain introduces severe high-frequency visual noise and aliasing, known as mipmap texture aliasing. When a block is located hundreds of meters away from the camera, its rendered screen projection spans only a fraction of a single screen pixel. If the GPU samples a full-resolution 16 by 16 texture for a sub-pixel screen area, tiny camera movements cause texels to flicker wildly, creating distracting visual noise across distant landscapes. To solve visual aliasing, the rendering engine builds mipmap pyramids for the texture atlas. A mipmap pyramid is a sequence of progressively downscaled lower-resolution versions of the texture atlas. Level 0 is the full-resolution atlas. Level 1 downscales the atlas by half along both axes using box filtering. Level 2 downscales Level 1 by half, continuing down to a 1 by 1 pixel mipmap level. During GPU rasterization, the fragment shader calculates the screen space derivative of the vertex UV coordinates, evaluating how rapidly UVs change across adjacent screen pixels. If a block is close to the camera, the GPU samples level 0 high-resolution texels. If a block is far away, the GPU automatically selects higher mipmap levels, sampling pre-filtered low-resolution textures. Mipmapping eliminates distant texture flickering, reduces GPU memory bandwidth consumption, and improves overall rasterization throughput. Furthermore, to maintain crisp texture clarity when viewing ground terrain at sharp, grazing angles, modern voxel engines combine mipmapping with anisotropic filtering. Standard trilinear filtering samples mipmaps using a square filter footprint, which blurs ground textures when viewed at steep perspective angles. Anisotropic filtering distorts the sampling footprint into an elongated ellipse aligned with the perspective view vector, preserving sharp texture detail along receding ground planes without introducing visual aliasing. However, even with VBO mesh batching, rendering every block face inside a solid chunk volume would choke GPU rasterization pipelines. Consider a solid chunk filled with stone from bedrock to sea level. The interior of the chunk contains thousands of stone blocks tightly packed together. If the engine built mesh geometry for every side of every block, the vast majority of rendered polygons would be internal faces completely hidden from the player's view. Rendering hidden interior geometry wastes massive amounts of GPU memory bandwidth and vertex shading processing power. To eliminate this waste, the graphics engine implements face culling algorithms. Face culling inspects every voxel before adding its geometry to the VBO mesh. For each block, the algorithm checks its 6 immediate cardinal neighbors: top, bottom, north, south, east, and west. If a neighbor block is completely solid and opaque, such as stone touching stone, the touching face is invisible to any possible camera perspective. The culling algorithm discards the face immediately, omitting its vertices from the VBO mesh. Only when a block face touches a transparent or non-solid voxel, such as air, glass, or water, does the algorithm generate vertices for that face. In a typical solid stone terrain volume, face culling discards over 90% of all potential block faces, shrinking VBO mesh size by an order of magnitude and allowing the graphics pipeline to process vast landscapes effortlessly. Face culling operates at the individual block level, but optimizing rendering across an entire world requires macro-scale camera optimizations, frustum culling and occlusion culling. The camera in a three-dimensional game engine defined by the player's view perspective sees the world through a geometric volume called the view frustum. The view frustum resembles a rectangular pyramid with its top chopped off, bounded by 6 mathematical planes: top, bottom, left, right, near, and far clipping planes. Frustum culling tests whether a chunk's spatial volume intersects the camera's view frustum before issuing draw calls. The engine encloses each 16 by 16 subchunk inside an axis-aligned bounding box, or ABB. On every frame, before rendering a subchunk, the CPU tests the 8 corners of its bounding box against the 6 frustum planes using vector dot products. If a subchunk lies completely behind the camera or to the far left outside the field of view, the frustum test fails, and the engine skips rendering that entire subchunk instantly, avoiding unnecessary GPU work. While frustum culling removes geometry outside the camera's field of view, it does not solve the problem of overdraw caused by objects blocking other objects. Imagine standing in front of a massive stone mountain. The subchunks inside and behind the mountain fall within your camera frustum planes, but they are completely hidden from sight by the mountain's front surface layer. Drawing those occluded subchunks wastes significant rasterization power. To prevent this, advanced voxel engines implement occlusion culling. Using algorithms like software rasterization or hardware occlusion queries, the engine tests whether a chunk's bounding box is hidden behind previously drawn opaque geometry. In a software rasterized occlusion system, the engine maintains a low-resolution depth buffer in CPU memory. It rasterizes coarse, bounding boxes of nearest chunks first. If a distant chunk's bounding box falls entirely behind filled pixels in the low-resolution depth buffer, the engine culls the distant chunk from the rendering queue. Occlusion culling ensures that underground cave networks and hidden valleys consume zero rendering overhead when blocked by foreground terrain. Beyond geometry rendering, a voxel engine requires a real-time lighting engine to calculate illumination levels across every block face. Voxel worlds feature dynamic lighting environments where sunlight streams down from the sky, torches illuminate deep caves, and redstone lamps flicker on and off. Calculating realistic lighting using traditional ray tracing or real-time shadow maps for millions of blocks was historically impossible on consumer hardware. Instead, voxel software architects invented discrete light propagation engines based on breadth-first search, or BFSQ algorithms. In a voxel light propagation engine, light is discretized into integer intensity levels ranging from 0, complete darkness, to 15, maximum brightness. Lighting data is stored in dedicated 4-bit nibble arrays attached to chunk structures, split into two independent channels, skylight and blocklight. Skylight measures direct sunlight penetration from the sky down toward the ground, while blocklight measures light emitted by artificial sources like torches, glowing obsidian, or lava. Skylight propagation begins at the top of the world. For every XZ column in a chunk, the engine scans downward from the maximum world height. As long as the algorithm encounters empty air voxels, it assigns the maximum skylight value of 15 to each voxel. The moment the skylight ray strikes an opaque block, full sunlight propagation stops, establishing the surface shadow boundary. Artificial block light, as well as skylight spreading sideways into caves, is calculated using a 3D breadth-first search flood fill queue. When a player places a torch, the block light value at those specific coordinates is set to 15. The engine pushes those block coordinates into a FIFO first-in, first-out lighting queue. The BFS light algorithm pops coordinates from the queue and inspects the 6 adjacent cardinal neighbor voxels. For each neighbor, the algorithm calculates the incoming light level by subtracting the target voxel's opacity decay factor from the source light level. Air has an opacity decay of 1, meaning light drops by 1 level per block traversed. Transparent blocks like water or tinted glass may have an opacity decay of 2 or 3, attenuating light faster. If the calculated light level is greater than the neighbor's current light value, the engine updates the neighbor's light nibble and pushes the neighbor's coordinates onto the BFS queue. The algorithm continues popping and spreading light outward in a spherical flood fill pattern until light attenuates to 0. When a player breaks or places a block, the light engine executes localized dynamic light updates. If a block is destroyed, opening a path for light, the BFS algorithm propagates new light outward from adjacent bright voxels. Conversely, if a player places an opaque block that cuts off a light source, the engine initiates a light removal pass. It pushes the darkened coordinates onto a removal queue, propagates light reduction outward by clearing affected neighbor voxels down to 0, and then executes a standard BFS repropagation pass from any remaining adjacent light sources to recalculate residual ambient light. Executing lighting through discrete integer BFS queues allows the engine to update complex light shifts across thousands of voxels in real time without touching expensive floating point GPU shader math. While discrete BFS integer lighting handles low overhead block illumination across vast landscapes, modern high-fidelity voxel engines supplement discrete lighting with advanced programmable shader pipelines, deferred shading architectures, cascaded shadow maps, and volumetric ray-marched fog. In early graphics engines, rendering was governed by forward rendering pipelines. In forward rendering, the CPU submits geometry meshes, and for every drawn polygon, the GPU fragment shader iterates through all active scene light sources, calculating diffuse, specular, and ambient lighting components for every pixel rasterized on screen. If a scene contains hundreds of dynamic point light sources, such as torches lining an underground tunnel, lava flows, glowing redstone lamps, and fire particle emitters, forward rendering collapses GPU performance. If a fragment shader evaluates 50 light sources across 3 million rasterized pixels, the GPU executes 150 million lighting calculations per frame. Furthermore, if opaque polygons overlap in screen space, forward rendering wastes massive GPU processing power shading pixels that are subsequently overwritten by foreground geometry. Modern voxel engines solve this lighting scale bottleneck by implementing deferred shading. Deferred shading separates geometry rendering from light calculation. The geometry pass fills a G buffer, a collection of screen space texture maps storing surface colors, normal vectors, and depth, while the lighting pass evaluates light sources in screen space without reshading hidden background polygons. Deferred shading decouples geometry rasterization from lighting calculations, splitting rendering into two distinct execution passes: the geometry pass and the lighting pass. In the first pass, the geometry pass, the engine draws scene geometry into a collection of screen space texture buffers known as the geometry buffer or G buffer. The G buffer is a multi-render target frame buffer holding 4 distinct 2D texture maps matching screen resolution, an albedo texture storing raw block surface color, a normal vector texture storing 3D surface normal vectors, a material property texture storing roughness, metalness, and emission flags, and a depth texture storing linear camera depth values. During the geometry pass, the GPU fragment shader executes minimal math. It samples the block texture atlas, writes surface properties directly into the G-buffer textures, and finishes. No light calculations are performed. Opaque geometry overwrites hidden background pixels in the G-buffer naturally through standard Z-buffer depth testing. In the second pass, the lighting pass, the engine renders a full-screen quad or bounding light volumes, passing the pre-filled G-buffer textures into the lighting shader. The fragment shader reads screen space position, surface normal, and albedo values directly from the G-buffer for each pixel, evaluating light attenuation only for visible pixels on screen. Deferred shading transforms lighting computational complexity from O(m*n), where m is polygon count and n is light count, down to O(p*n), where p is the number of screen pixels. Adding hundreds of dynamic torch lights or lava glows deep in cave networks consumes a constant, predictable GPU processing time proportional strictly to screen resolution, enabling lush visual environments with zero geometry overdraw penalty. To complement deferred shading with realistic real-time sun and moon shadows, the engine incorporates cascaded shadow maps, known as CSM. Standard shadow mapping renders scene depth from the light source's perspective into a 2D depth texture, comparing camera pixel depth against shadow map depth to determine whether a point is in shadow. However, applying a single shadow map texture across an infinite voxel world leads to severe visual shadow aliasing. Near the camera, shadow map pixels stretch over large screen areas, producing blocky, pixelated shadow edges, while far away from the camera, shadow map resolution is wasted on tiny background terrain. Cascaded shadow maps solve shadow aliasing by partitioning the camera view frustum along the depth z-axis into multiple contiguous shadow cascade slices, typically near, medium, and far cascades. The engine renders a separate depth shadow map for each cascade slice from the sun's directional light perspective. The near cascade covers space from 0 to 20 meters in front of the camera, allocating high shadow map resolution to near-surface geometry. The medium cascade covers 20 to 80 meters, while the far cascade spans 80 to 300 meters. During pixel shading, the GPU fragment shader selects the appropriate shadow cascade map based on the pixel's camera depth, sampling high-resolution shadows close to the player while maintaining broad shadow coverage across distant mountain ranges. To eliminate harsh, unnatural shadow boundaries, the shader applies percentage closer filtering, or PCF, sampling a grid of surrounding shadow map texels and blending depth comparisons to generate soft, natural shadow edges. Finally, to create breathtaking atmospheric immersion, such as sunlight shafts streaming through dense forest canopies or thick underground mist hovering over lava lakes, the engine implements volumetric ray-marched atmospheric fog. Standard distance fog simply blends pixel colors toward a solid sky color based on camera distance, producing flat, unrealistic atmospheric depth. Volumetric fog calculates real-time light scattering through 3D atmospheric density fields using GPU ray-marching shaders. The fragment shader casts a ray from the camera position through each screen pixel into 3D world space, stepping along the ray vector in discrete spatial increments. At each ray-marching step, the shader samples a 3D procedural noise field to determine local fog density, queries the cascaded shadow map to test whether the spatial point is illuminated by sunlight or blocked by terrain geometry, and evaluates the Henny-Greenstein phase function to compute forward light scattering toward the camera lens. The shader integrates light scattering and Beer-Lambert extinction along the ray path, accumulating atmospheric luminance. Where sunlight streams through gaps in leaf foliage, the ray marcher accumulates high light scattering, rendering volumetric God rays dancing through mist. Volumetric ray marching turns open sky and subterranean caverns into dynamic, painterly atmospheric environments. Complementing terrain VBO rendering, deferred shading, and volumetric fog is the entity rendering engine and particle simulation subsystem. Drawing static terrain blocks relies on baked VBO subchunk meshes, but dynamic entities such as players, hostile mobs, passive animals, and floating item drops move continuously, requiring dynamic vertex transformation, skeletal animation, and particle pooling pipelines. Rendering hundreds of animated entities simultaneously presents a distinct CPU-GPU bottleneck. In traditional skeletal animation systems, an entity's mesh is bound to a hierarchical bone structure. The CPU calculates skeletal bone transformation matrices, combining joint rotation quaternions, translation vectors, and scale factors, and applies matrix vector multiplication for every vertex in CPU memory before uploading transformed vertices to the GPU. Executing CPU-side vertex skeletal transformations for hundreds of active mobs on every frame saturates CPU execution and floods the PCI Express bus with dynamic vertex transfers. To eliminate CPU skeletal overhead, voxel engines implement skeletal matrix palette instancing. Under skeletal matrix palette instancing, entity mesh geometry is stored on the GPU inside static, shared VBOs containing untransformed model pieces, such as head, torso, arm, and leg boxes. Each vertex includes a bone index attribute specifying which skeletal joint governs its movement. On every render frame, the CPU calculates compact 4x4 transformation matrices only for active skeletal joints, uploading a small bone matrix array, the matrix palette, to GPU uniform buffer objects, or UBOs. The vertex shader reads the bone index attribute, retrieves the corresponding bone matrix from the UBO matrix palette, and executes matrix vector transformation directly on the GPU's massively parallel compute units. Furthermore, when rendering identical mob types, such as a horde of 20 zombies, the engine utilizes GPU-instanced rendering, GL-drawElements instanced. The CPU uploads an array of per-instance data containing world position vectors, partial tick interpolation offsets, and matrix palette IDs, issuing a single instance draw call. The GPU rasterizes all 20 zombie models in a single draw command, transforming individual instances in parallel and shrinking CPU draw call overhead to near zero. Alongside skeletal mob rendering, the engine executes real-time particle simulation for visual effects. Campfire smoke, lava sparks, underwater bubbles, explosion debris, splash droplets, and enchantment sparkles. Simulating and rendering thousands of dynamic particles can easily trigger severe garbage collection pressure and rendering bottlenecks if not architected correctly. To prevent memory allocation overhead, the particle engine uses object pooling and primitive array allocation. At engine startup, the particle manager pre-allocates a fixed capacity object pool containing thousands of reusable particle instances. When an explosion or lava pop occurs, the particle engine does not instantiate new objects on the heap. Instead, it claims inactive particle instances from the pool, initializes their position vectors, velocity vectors, lifespan counters, and color floats, and registers them in the active particle execution queue. When a particle's lifespan expires, the engine resets its state and returns it to the pool for instant recycling, achieving zero heap allocations during heavy combat or environmental effects. Rendering thousands of individual particles is optimized using billboard quad orientation. A particle is represented geometrically as a simple 2D square quad comprised of 4 vertices and 2 triangles. To ensure that 2D particle quads always face the player's view perspective regardless of camera angle, the vertex generator applies billboard matrix rotation. The generator retrieves the camera's right vector and up vector from the active view matrix. It calculates the 4 particle corner vertices by multiplying the particle's spatial origin coordinate by the camera right and up vectors scaled by particle size. Billboard quad rotation executes in the vertex shader or CPU geometry pass, ensuring that smoke puffs, flame sparks, and magic sparkles maintain perfect 2D orientation toward the lens as the player rotates the camera. Combining matrix palette instancing for skeletal mobs with object-pooled billboard particle rendering allows voxel engines to display vibrant, action-packed worlds filled with hundreds of active entities and thousands of dynamic environmental particles at maximum frame rates. Alongside geometry rendering and BFS light propagation, the client engine incorporates a 3D spatial audio engine to render immersive environmental soundscapes. In a 3-dimensional voxel world, audio is not merely background stereo music. Sound events, such as footsteps on stone, water trickling, lava popping, creeper fuses hissing, or mob growls, provide essential spatial cues informing the player of unseen threats deep in cave networks. The spatial audio engine interfaces with low-level audio APIs, such as OpenAL or FMOD, to manage 3D sound positioning, distance attenuation, and Doppler pitch shifting. Sound sources are registered as point emitters in world space, defined by 3D position vectors, velocity vectors, gain multipliers, and sound sample buffers. The player's camera perspective acts as the spatial audio listener, defined by an ear position vector, a forward view vector, and an up vector. On every render frame, the audio engine updates listener position and orientation vectors in OpenAL, allowing the hardware sound mixer to calculate panning gains across stereo speakers or surround sound headphones. Distance attenuation is calculated using the inverse distance clamped model. When a sound emitter triggers, the audio engine computes the Euclidean distance vector between the sound source coordinates and the listener ear coordinates. As distance increases, sound gain attenuates according to the inverse distance formula, dropping volume smoothly until reaching the maximum audibility threshold, typically 16 blocks for footsteps and 64 blocks for thunder or explosions. However, rendering realistic 3D audio inside dense voxel landscapes requires solving the problem of acoustic sound occlusion. If a zombie growls on the opposite side of a 10-block-thick solid stone wall, playing the sound at full unattenuated volume confuses the player, making the zombie sound as if it were standing in the same open room. In real-world physics, solid stone walls absorb and muffle acoustic sound waves. To simulate acoustic wall damping, advanced voxel audio engines implement sound occlusion raycasting. When a sound event triggers, the audio engine casts short occlusion rays between the sound emitter position and the camera listener position. The occlusion algorithm checks block states along the ray path using 3D DDA traversal. For every solid block intersected by the sound ray, such as stone, dirt, or wood, the audio engine applies an occlusion gain penalty and a low-pass frequency filter. Stone applies high occlusion damping, absorbing high-frequency sound waves and muffling the audio, while air or transparent glass allows sound waves to pass freely. Furthermore, if the camera listener is submerged underwater, the audio engine toggles global underwater DSP filters. Low-pass biquad filters attenuate high frequencies across all sound channels, while environmental reverb algorithms simulate subaquatic acoustic resonance. Integrating 3D spatial positioning, raycasted block occlusion, and dynamic DSP filtering creates a rich, believable acoustic atmosphere that mirrors the physical geometry of the voxel environment. Having established how lighting and spatial chunks are processed in active memory, we must now address one of the most complex architecture challenges in game engineering: data persistence and file storage formats. A real-time voxel engine is effectively a highly specialized spatial object relational database. Every player movement, inventory change, redstone state, and terrain modification must be saved permanently to disk so that the world state can be stored seamlessly across game sessions. However, serializing millions of dynamic voxels and entity states without freezing the main game loop or exhausting storage drive bandwidth requires dedicated binary file formats and storage pipelines. The fundamental serialization format invented for voxel engine persistence is named binary tag, commonly known as NBT. Named binary tag is a lightweight, type-prefixed hierarchical binary format designed specifically for structured data tree storage, where every data field is prefixed with an explicit type byte and keystring name, allowing high-speed binary stream reading without parsing human-readable text. In web and enterprise software development, data interchange formats like JSON or XML are widely used because they are human-readable. However, text-based formats like JSON are terribly inefficient for real-time game engines. Parsing text strings requires heavy CPU string allocation, character scanning, and floating-point conversion logic. Furthermore, text formats incur massive storage overhead. Storing a simple integer in text requires 1 byte per character digit, whereas binary formats store integers directly in 4 native byte words. NBT solves this by operating as a strict binary stream format. Every data field in an NBT payload begins with a single byte identifier specifying its data type, followed by a UTF-8 string defining its field key name, followed immediately by the raw binary payload data. The format defines 13 primitive and container tag types: tag end, tag byte, tag short, tag int, tag long, tag float, tag double, tag byte array, tag string, tag list, tag compound, tag int array, and tag long array. To visualize the hierarchical elegance of NBT, imagine a complex block entity, such as a furnace burning or deep underground. The engine represents this furnace as a tag compound, which as a key-value dictionary mapping string keys to arbitrary NBT tags. Inside the furnace tag compound, the key burn time maps to a tag short storing a 2-byte integer of remaining fuel ticks. The key cook time maps to a tag short tracking smelting progress. The key items maps to a tag list containing individual tag compounds for each inventory slot. Each slot tag compound contains a tag string for the item ID, a tag byte for the stack count, and a tag short for damage values. Because NBT uses explicit length prefixes for arrays and strings, the binary deserializer never needs to scan strings for closing quotes or delimiter tokens. When an NBT reader encounters a tag byte array representing a chunks block palette indices, it reads a 4-byte integer specifying the exact array length, and then executes a single bulk memory read operation, copying thousands of raw bytes directly from the file stream into JVM heap arrays. This raw binary stream processing allows the engine to parse complex entity states and player profiles in microseconds. While NBT solved individual object serialization, early voxel engines suffered from a catastrophic storage file system bottleneck known as the individual chunk file design. In early engine iterations, every 16 by 16 chunk was saved to disk as an independent file, named according to its spatial coordinates and compressed using gzip. A single chunk file was placed inside a nested folder hierarchy on the operating system's file system. At first glance, saving each chunk as an isolated file seems logically clean. When the player enters a chunk, the engine opens that specific file. When the player leaves, the engine writes and closes that specific file. However, in practice, the individual chunk file architecture caused severe storage performance degradation across operating systems. To understand why saving thousands of tiny individual files broke operating system file systems, we must examine how storage drives and file systems manage disk sector allocations. Operating system file systems, such as NTFS on Windows, Extension 4 on Linux, or FAT32 on legacy drives, organize disk storage into fixed-size clusters, typically 4 kilobytes in size. If a small chunk file contains only 1 kilobyte of data, the file system allocates an entire 4 kilobyte cluster to that file, wasting 3 kilobytes of physical disk space. Multiplying this sector overhead across hundreds of thousands of chunk files in an explored world resulted in massive storage drive bloat. Furthermore, operating systems maintain directory index structures and a node metadata tables to track every file on disk. When a world directory contained 50,000 individual chunk files, performing basic file system operations, such as listing directory contents, opening files, or copying a world save, stalled the operating system. Every time the engine loaded a new view distance, it issued hundreds of separate OS file open, read, and close system calls. On traditional spinning magnetic hard drives, each file open command forced the physical drive head to execute a mechanical seek across disk platters to locate file system metadata, causing severe disk read latency. The main game thread frequently froze while waiting for the operating system file system driver to resolve hundreds of tiny file handles. Software architects completely resolved this storage crisis by inventing the region file format, known as the Anvil storage system. Region files are spatial container files that aggregate 1024 individual chunk files into a single file on disk, preventing operating system file systems from slowing down under millions of small individual files. The core architectural insight of region files is spatial aggregation. Instead of storing every 16 by 16 chunk as an isolated file on disk, the engine groups a 32 by 32 grid of chunks, encompassing 1024 individual chunks, into a single consolidated container file called a region file, identified by the file extension .mca. A single region file represents a vast spatial territory measuring 512 blocks along the x-axis and 512 blocks along the z-axis. By grouping 1024 chunks into a single file, the total number of files in a world directory drops by a factor of 1000, completely eliminating file system metadata bloat, inode exhaustion, and OS file handle latency. To manage 1024 chunks inside a single binary region file without creating file lock contention or sequential scanning bottlenecks, the region file format incorporates an internal sector allocation table. A region file is structured as a continuous sequence of fixed-size 4 kilobyte sectors. The very first 4 kilobyte sector at the beginning of a region file is the location offset table. This 4 kilobyte sector contains exactly 1024 4-byte integer entries, corresponding to each chunk position in the 32 by 32 grid. The entry index is calculated instantly from local chunk coordinates using spatial flattening math. Each 4-byte entry in the location offset table contains 2 packed binary integers. The first 3 bytes define the starting sector offset of the chunk within the region file, and the 4th byte defines the total number of contiguous 4 kilobyte sectors allocated to that chunk. The second 4 kilobyte sector in the region file is the timestamp table, containing 1024 4-byte integers recording the exact epoch timestamp when each chunk was last saved to disk. Following these 2 header sectors, the remainder of the region file consists of binary data sectors housing the actual compressed NBT chunk payloads. When the engine needs to load chunk X10, Z15, it opens the corresponding region file, reads the single 4-byte entry at index offset in the header sector, shifts the byte value to extract the starting sector number, seeks directly to that sector offset, and reads the chunk payload. This operation requires only 2 fast disk reads, 1 read of the header sector and 1 continuous block read of the chunk data payload, completely bypassing file system directory index searches. Managing variable-size chunk data inside a fixed sector region file requires dynamic sector allocation and defragmentation algorithms. As players modify a chunk, placing complex redstone mechanisms or tile entities, the compressed size of that chunk's NBT payload expands or shrinks. If a chunk's compressed payload fits within 4 kilobytes, it occupies a single sector. If a massive player build expands the compressed payload to 5 kilobytes, the payload exceeds a single sector and requires 2 contiguous 4 kilobyte sectors, total 8 kilobytes. When saving an expanded chunk, the region file manager checks whether the chunk can expand safely into adjacent sectors. If adjacent sectors are already occupied by neighboring chunks, the manager marks the old sectors as free in an in-memory sector allocation bitmap, allocates a new continuous block of free sectors elsewhere in the file, writes the payload, and updates the 3-byte sector offset in the location header. To prevent disk drive wear and maximize storage throughput, Region files combine sector packing with on-the-fly streaming compression using zlib and gzip pipelines. Raw uncompressed NBT chunk data, containing uncompressed block arrays, light nibbles, and tile entities, can easily exceed 100 kilobytes per chunk. Passing raw 100 kilobyte streams over disk buses for thousands of chunks would saturate storage drive write queues. Before writing a chunk payload to a region file sector, the engine passes the serialized NBT byte stream through a zlib deflate compression pipe. Zlib compression scans the byte stream for repeating patterns and contiguous sequences of identical values. Because voxel chunks contain massive uniform volumes of stone, dirt, or air, the LZ77 sliding window and Huffman coding algorithms inside zlib achieve extraordinary compression ratios. A raw 100 kilobyte chunk byte stream compresses down to 3 or 4 kilobytes, fitting neatly into a single 4 kilobyte region file sector. When the chunk is loaded later, the engine reads the compressed sector payload from disk, passes it through a zlib inflate decompression pipe, and reconstructs the uncompressed NBT structure in memory. This introduces a fundamental software engineering trade-off: trading CPU compute cycles for disk storage bandwidth. Decompressing zlib data consumes CPU clock cycles on worker threads, but because modern multi-core CPUs operate exponentially faster than physical disk storage I/O, spending CPU cycles to shrink payload sizes yields a massive net performance gain, accelerating chunk load speeds by several 100%. Now that we understand persistence, region file structures, and compressed I/O streams, we can examine the hidden background engine operations that execute continuously during active gameplay and sleeping cycles. When a player lies down in an in-game bed to sleep, the world appears to pause visually, instantly fading to black and transitioning from dusk to dawn. However, behind this simple visual fade lies a complex sequence of concurrent background tasks executed by the server simulation engine. When all active players in a world enter a bed, the server engine initiates time fast-forwarding logic. World time in a voxel engine is driven by a 64-bit long integer tick counter that increments by 1 on every 20 Hz tick cycle. A complete in-game day-night cycle spans 24,000 ticks, or 20 minutes of real-world time. Day lasts 12,000 ticks, dusk lasts 1,000 ticks, night lasts 9,000 ticks, and dawn lasts 1,000 ticks. When players sleep, the server does not simply jump the time tick counter forward by 12,000 ticks in a single instant. Doing so would break time-dependent entity schedules and redstone clock circuits. Instead, the engine rapidly accelerates the world tick counter over a series of brief transition frames, advancing time towards 0 ticks, representing morning, while processing essential background subchunk updates. During each server tick, whether standard or fast-forwarded, the engine executes random tick updates across all active subchunks within player simulation range. Traversing every single block coordinate in every loaded chunk on every tick would require evaluating millions of voxels 20 times per second, paralyzing CPU execution. To optimize environmental updates, the engine implements random subchunk sampling. On each tick, for every active 16 by 16 by 16 subchunk, the engine selects a small, fixed number of random voxel coordinates, typically 3 blocks per subchunk, using fast pseudorandom integer math. It inspects the block state at those 3 chosen coordinates. If the block is a crop like wheat or potatoes, the engine checks light levels and applies a growth stage increment. If the block is a sapling, it evaluates surrounding space and triggers tree generation. If the block is leaf geometry detached from a wood log trunk, the engine initiates a leaf decay algorithm, dissolving the unattached leaf block into drop items. If the block is ice exposed to high light levels, it melts into liquid water. This random tick sampling model provides the illusion of continuous organic world simulation across millions of blocks while consuming a tiny, constant slice of CPU budget per tick. Simultaneously, the background simulation engine manages weather progression, redstone circuit pulse queues, and entity population caps. Weather state is governed by independent global timer counters for rain and thunder. When a rain timer expires, the server toggles global precipitation flags, altering sky lighting values, increasing crop hydration rates, and updating fire block extinguishment sweeps across surface chunks. Entity management during background processing is governed by strict population cap algorithms. To prevent entity clutter from consuming system memory, the engine categorizes entities into distinct mobs groups: hostile monsters, passive animals, ambient creatures, and aquatic life. For each category, the server enforces a mathematical cap proportional to the number of loaded chunks within player activation radius. Before spawning new entities, the background loop calculates current entity counts across loaded chunks. If hostile monster counts fall below target caps, the engine executes spawning sweeps, selecting random surface and cave voxels near players, testing light levels and collision-bounding boxes, and instantiating mob entities. Conversely, when players sleep or move far away, the background engine calculates Manhattan distance vectors from players to active mobs. Hostile mobs positioned beyond 32 blocks enter a random pawn evaluation queue, while mobs positioned beyond 128 blocks are instantly evicted from memory, maintaining strict heap safety. While world logic ticks continuously on the primary server thread, persistence requires saving modified world states to region files without interrupting the player's real-time experience. In early engine designs, saving the world caused severe frame freezes known as save lag spikes. The server thread halted world simulation, iterated through loaded chunks, serialized NBT data, and executed synchronous disk writes. If disk I/O was slow, the server thread stalled for hundreds of milliseconds, dropping frames and causing input lag. Modern voxel architectures eliminate save lag through asynchronous copy-on-write autosaving. Copy-on-write makes an instant pointer-clone snapshot of dirty chunk memory when autosaving triggers, allowing live game simulation to continue modifying terrain while background worker threads write the frozen snapshot to disk. The autosave system decouples memory serialization from physical disk I/O using dedicated worker thread pools and copy-on-write state snapshots. To visualize copy-on-write autosaving, consider a chunk that has been modified by a player breaking stone and placing chests. The chunk manager marks this chunk with a dirty flag. When the scheduled autosave checkpoint triggers, typically every 45 seconds, the server main thread scans loaded chunks for dirty flags. Instead of writing data directly to disk on the main thread, the server thread performs an instant in-memory snapshot of the dirty chunks block array and NBT entity tags. In computer science, a copy-on-write snapshot clones the underlying primitive data pointers or array references in a fraction of a microsecond. The main server thread then clears the dirty flag on the active chunk, allowing game simulation and player block edits to continue immediately without pausing. The copied snapshot payload is passed to an asynchronous I/O queue managed by background worker threads. The worker threads execute zlib-deflate compression, parse region file sector headers, allocate target sectors, and write the binary payload to disk completely in the background. If a player places a new block on the active chunk while the background thread is writing the snapshot to disk, the edit mutates only the active memory array, leaving the background snapshot untouched. Asynchronous copy-on-write autosaving guarantees that heavy disk persistence operations execute concurrently on separate CPU cores, eliminating autosave frame spikes entirely. Alongside disk autosaving, the background processing engine continuously manages memory cleanup, garbage collection ergonomics, and cache eviction across system RAM. As a player travels thousands of blocks across a procedurally generated world, the engine constantly loads new chunks ahead of movement and unloads old chunks left behind. If chunk memory is not reclaimed aggressively, heap allocations grow continuously until system memory is exhausted, resulting in an out-of-memory crash. To manage loaded chunk memory footprint, the engine utilizes least recently used, or LRU, cache eviction algorithms. The chunk manager maintains an in-memory spatial cache map indexing loaded chunks by spatial coordinates. Every time a chunk is accessed by rendering, physics, or entity AI, the engine updates its access timestamp. When the total loaded chunk count exceeds the maximum target capacity determined by the user's view distance setting, the LRU eviction manager triggers a cleanup sweep. It scans the cache map, identifies chunks with the oldest access timestamps located farthest outside the player's activation radius, serializes any dirty state, unregisters their VBO rendering meshes, and evicts them from the active spatial map. However, in Java-based engine environments, simply removing an object reference from a map does not instantly free system RAM. The memory remains allocated until the Java garbage collector executes a garbage collection sweep. To optimize memory reclamation, modern engines utilize weak reference and soft reference wrappers for heavy cached assets like pre-baked chunk render meshes and terrain light maps. A weak reference allows the engine to maintain a reference to an object in memory without preventing the garbage collector from reclaiming it when heap pressure rises. If the JVM approaches heap memory limits, the garbage collector automatically clears weak references, instantly freeing megabytes of cached VBO vertex data and compressed light nibbles before an out-of-memory error can occur. Furthermore, enterprise voxel engine deployments optimize garbage collection performance by tuning the garbage-first garbage collector, known as G1GC. G1GC divides the JVM heap into thousands of equal-sized memory regions, ranging from 1 megabyte to 32 megabytes. G1GC tracks object allocation rates and heap fragmentation in real time, executing concurrent background sweeps that compact fragmented regions with minimal stop-the-world pause times. By pairing LRU chunk eviction caches with weak reference wrappers and G1GC region tuning, the background processing engine maintains stable memory footprint and butter-smooth 60 frames per second rendering over multi-hour exploration sessions. To appreciate how background processing integrates with internal world logic, we must deconstruct the subsystems that execute during active server ticks: the Redstone Circuit Simulation Engine, the Voxel Pathfinding Engine, and the Network Delta Compression Protocol. These systems demonstrate how high-level game mechanics are powered by rigorous graph theory, spatial searching, and network bandwidth optimization. The Redstone Circuit Engine is fundamentally a discrete, spatial logic gate simulator operating within a three-dimensional grid. Redstone components, such as dust, repeaters, comparators, torches, and pistons, allow players to build Turing-complete digital computers inside the voxel world. Evaluating thousands of active logic gates across loaded chunks without degrading tick performance requires framing circuit propagation as a directed acyclic graph, or DAG, evaluated via event-driven tick queues. In a Redstone engine, Redstone dust conducts a discrete signal strength ranging from 0 to 15. Signal strength attenuates by 1 unit for every block of dust traversed. To extend signals beyond 15 blocks or introduce directional logic delays, players use repeaters. Repeaters act as signal diodes and delay buffers, boosting signal strength back to 15 while introducing a configurable delay of 1 to 4 server ticks. When a Redstone power source, such as a lever or pressure plate, changes state, the engine does not reevaluate the entire world's Redstone network. Doing so would turn circuit processing into an expensive ON global scan on every tick. Instead, the engine implements an event-driven observer pattern. When a power source toggles, it emits a block update event to its immediate cardinal neighbors. Each neighbor component evaluates its input state, calculates its new output signal, and if its output changes, pushes a circuit update task onto the server's scheduled tick queue. Repeater delays are managed by a multi-ring tick scheduler. If a repeater is configured for a 2-tick delay, the server pushes the repeater's activation event into a ring buffer bucket scheduled 2 ticks in the future. When the server tick loop reaches that target tick, it pops the scheduled events from the ring buffer and propagates power to downstream components. However, complex Redstone circuits introduce topological graph challenges, such as microtick ordering and update loops. If 2 torches power the same wire, the order in which update events are processed dictates circuit output. In early engine iterations, updating Redstone based on arbitrary hash map iterator orders caused directional circuit behavior, where identical circuits executed differently depending on whether they faced north or east. Modern Redstone architectures resolve this by organizing update events into deterministic topological sort queues. When power propagates, the engine constructs a localized directed acyclic graph of active components, sorting update execution by dependency depth and coordinate hashes. This guarantees that digital adders, memory registers, and logic gates execute deterministically regardless of spatial orientation. To master Redstone architecture like a staff software engineer, we must examine advanced component state evaluation, comparators, quasi-connectivity, and fluid flow simulation. Redstone is not merely a toy wiring system. It is a full-fledged, discrete spatial signal processing framework. Consider the Redstone comparator. A comparator is a complex dual-mode logic gate featuring 2 inputs: a primary signal input at the rear, signal A, and 2 side inputs, signal B. The comparator evaluates these inputs in real time according to 2 operational modes: comparison mode and subtraction mode. In comparison mode, the comparator tests whether signal A is greater than or equal to the maximum of the side inputs, signal B. If signal A is greater or equal, the comparator outputs signal A unchanged. If signal A is less than signal B, the comparator outputs 0. In subtraction mode, the comparator performs discrete arithmetic. It calculates signal A minus signal B, outputting the difference, clamped at a minimum of 0. Furthermore, comparators possess the unique ability to read internal block state data from adjacent container tile entities, such as chests, furnaces, hoppers, or jukeboxes, without opening an inventory GUI screen. When placed adjacent to a chest, the comparator queries the chest's tile entity NBT item array. It calculates inventory fullness by summing item stack counts across all slots and dividing by total container capacity, scaling the result to a discrete signal strength ranging from 0 to 15. This inventory signal reading mechanism allows players to build automated item sorting networks, storage telemetry monitors, and complex state machines. Beyond comparators, one of the most fascinating spatial phenomena in Redstone engine history is quasi-connectivity. Quasi-connectivity, commonly known as QC, is a famous software behavior where certain mechanical blocks, such as pistons, droppers, and dispensers, can be powered by redstone signals located 2 blocks above them or diagonally adjacent to their upper boundary, even when there is no direct wire connection touching the block itself. To understand why quasi-connectivity exists, we must analyze the historical code inheritance of block update bounds. In early voxel engine versions, door blocks occupied a 2-block-high vertical volume. When a redstone signal touched the upper half of a door, the door code checked for power at the upper block coordinate and updated both the top and bottom door halves simultaneously. When pistons, droppers, and dispensers were subsequently implemented, their spatial power check logic inherited the exact same upper block update check offsets previously written for 2-block-high doors. Consequently, a piston checks for power at its own coordinate as well as the spatial coordinate directly above it. However, a piston only executes its extension movement when it receives a block update event. If a redstone wire turns on 2 blocks above a piston, the piston detects the power in its upper check logic. But if the wire is not directly adjacent, no block update event is triggered to wake up the piston. The piston enters a dormant, quasi-powered state. The instant any adjacent block changes state, such as a player placing a block, grass growing, or a nearby block breaking, it fires a local block update event. The dormant piston receives the update event, reevaluates its spatial power state, detects the quasi-power signal from above, and fires its extension arm instantly. Engineers exploited this quasi-connectivity code behavior to create block update detectors, known as BUD switches. A BUD switch holds a piston in a dormant quasi-powered state until an environmental block update, such as a crop growing, water freezing, or a furnace turning off, triggers the piston. BUD switches turn the voxel world into an interactive sensory mesh, enabling automated farms, trap triggers, and secret door mechanisms. Alongside redstone logic, the server engine simulates environmental liquids using discrete cellular automata fluid dynamics. Fluid simulation across infinite voxel terrain presents a major computational challenge. Calculating continuous Navier-Stokes fluid dynamics for flowing rivers and ocean tides would paralyze real-time server tick execution. Voxel software architects resolve fluid rendering and physics by modeling liquids, water, and lava as discrete cellular automata governed by integer decay levels and directional flow vectors. Water blocks possess a fluid state property ranging from level 0, a stationary source block, to level 7, the weakest flowing edge stream. On every fluid tick, the engine inspects active liquid voxels and evaluates neighboring spatial blocks. Fluid flow follows a strict priority algorithm. First, the engine checks whether the spatial voxel directly below the liquid block is air or non-solid. If the voxel below is open, the liquid flows straight down, spawning a new vertical fluid block at level 0 with maximum downward momentum. If the voxel below is solid, the liquid attempts to spread horizontally onto adjacent cardinal neighbor blocks. To determine flow direction, the engine executes a local breadth-first search slope detection algorithm. The BFS algorithm scans surrounding terrain within a 4-block radius to identify the nearest spatial drop-off or elevation drop. If the search locates a drop-off 3 blocks to the east, the fluid engine calculates a horizontal flow vector pointing east, propagating water toward the slope drop. If no nearby drop-offs are found, the liquid spreads uniformly in all 4 cardinal directions, decreasing its fluid decay level by 1 unit for each block traversed. Once the decay level reaches 7, horizontal flow stops. Furthermore, the fluid engine incorporates dynamic state machine interactions between water and lava. When a flowing water voxel touches a stationary lava source block, the engine transforms the lava source into obsidian, a nearly indestructible block. When flowing water touches flowing lava streams, the engine transforms the lava into cobblestone or smooth basalt. To prevent infinite fluid cascading loops from choking CPU execution when massive oceans flood subterranean caves, the engine maintains a fluid update queue. Fluid updates are throttled by scheduled tick delays. Water ticks every 5 server ticks, 200 milliseconds, while thick, viscous lava ticks every 30 server ticks, 1500 milliseconds. In the overworld, discrete cellular automata fluid rules allow voxel engines to simulate massive flowing rivers, waterfalls, and lava lakes at real-time tick rates. Alongside circuit evaluation, the server engine processes entity artificial intelligence through the 3D voxel pathfinding engine. In standard 2-dimensional games, pathfinding relies on flat grid navigation maps. In a fully destructible voxel world, entities must navigate complex 3-dimensional terrain, stepping over obstacles, jumping across gaps, swimming through water, and avoiding open drop-offs or lava pits. Voxel pathfinding is powered by specialized adaptations of the A** search algorithm. A* finds the shortest path between a starting coordinate and a destination coordinate by evaluating a heuristic function estimating remaining distance. The total path cost f is defined as cost g, the actual distance traveled from the start, plus cost h, the estimated Euclidean or Manhattan distance to the target. To execute A* on a voxel grid, the pathfinder treats every walkable block as a graph node. For a node to be considered walkable, the engine tests spatial clearance. The block below must be solid to support weight, while the 2 blocks above must be air or non-solid to accommodate entity height bounding boxes. During path evaluation, the algorithm pops the lowest cost node from an open priority queue and inspects its 26 surrounding spatial neighbors in 3 dimensions. For each neighbor, the engine evaluates movement cost penalties based on environmental hazards. Walking over grass incurs standard cost. Swimming through water increases movement cost due to fluid drag, while stepping onto magma blocks or open drop-offs incurs massive cost penalties, steering the entity path away from danger. To prevent pathfinding from stalling the server tick thread when hundreds of entities navigate simultaneously, software architects implement spatial path caching and hierarchical navigation graphs. When an entity targets a distant location 50 blocks away, the engine does not compute a complete 50-block voxel path instantly. Doing so requires evaluating thousands of potential spatial nodes. Instead, the pathfinder constructs a coarse, hierarchical navigation graph, dividing space into 16 by 16 chunk regions. It identifies high-level spatial portals, such as mountain passes, tunnels, or bridges, connecting adjacent chunks, and plans a macro path across chunk portals. Once the macro path is established, the entity computes detailed voxel-level A-star paths only for its immediate local chunk sector. As the entity moves, worker threads asynchronously compute the next sector path, distributing pathfinding CPU loads smoothly across tick cycles. While local world simulation processes circuits and AI paths, multiplayer servers must stream world state changes to connected clients across real-world internet networks. Streaming an uncompressed world state over TCP or UDP sockets would quickly saturate client network bandwidth, causing extreme latency and packet loss. To minimize network bandwidth, voxel engines implement network delta compression and spatial interest management protocols. The client-server network layer operates on the principle of minimal state replication. The server sends only what the client can see and sends only what has changed since the last network tick. Spatial interest management organizes clients into spatial subscription zones. The server tracks each connected player's chunk coordinates. A client receives network packets exclusively for chunks located within its defined network view distance radius. If a creeper explodes 10 chunks away outside a player's view radius, the server omits those block updates from that client's network stream, preventing unnecessary bandwidth consumption. For entities and blocks within view, the server applies delta compression. Rather than broadcasting an entity's absolute double precision 64-bit X, Y, and Z coordinates on every tick, which consumes 24 bytes per entity, the server transmits 16-bit integer relative movement deltas, representing how many fractional steps the entity moved since the previous tick. A relative movement byte packet consumes less than 4 bytes, shrinking entity network traffic by over 80%. Furthermore, entity rotations are encoded as single-byte binary angles. A full 360-degree circle is mapped into a single 8-bit and signed byte ranging from 0 to 255, providing a rotational resolution of 1.4 degrees per step. For visual orientation, 1.4 degrees of precision is completely imperceptible to human eyes. Yet encoding rotation in a single byte saves millions of bytes per second across active multiplayer servers. To manage high concurrency client connections and network buffer allocations without stalling the main server tick loop, modern voxel multiplayer servers implement non-blocking event-driven network frameworks, exemplified by Netty pipelines. Netty utilizes asynchronous Java NIO, non-blocking input-output selectors, allowing a small pool of network I/O worker threads to manage thousands of active client socket channels concurrently. Network packet processing is organized as a sequential pipeline of channel handlers: byte-to-message decoder, packet decompressor, packet decryptor, packet deserializer, and packet inbound handler. When a binary packet arrives from a client socket, Netty allocates an off-heap direct bytebuf buffer. Allocating off-heap direct bytebuf buffers bypasses Java heap memory entirely. The network operating system kernel writes socket data directly into native off-heap memory address pointers via direct memory access, known as DMA. This eliminates intermediate buffer copies between OS kernel space and the JVM heap, reducing network serialization latency to single-digit microseconds. To minimize packet payload sizes across network streams, the binary protocol utilizes varint and varlong variable length integer encoding. In standard programming languages, a standard integer consumes 32 bits for bytes, regardless of whether its numeric value is 1 or 1 billion. Storing small numbers like block state IDs, slot indices, or entity IDs in 4-byte integers wastes significant network bandwidth. Variant encoding compresses integers using variable 7-bit byte chunks. The lowest 7 bits of each byte store raw binary payload value, while the most significant 8th bit, the most significant bit, or MSB, acts as a continuation flag. If the integer value is less than 128, the continuation flag is set to 0, and the variant consumes exactly 1 byte on the wire. If the value exceeds 128, the continuation flag is set to 1, indicating that the reader must read the subsequent byte to reconstruct the complete integer. For small integer values, which constitute over 90% of all network packet fields, variant encoding shrinks field sizes from 4 bytes down to a single byte, achieving a 75% network bandwidth reduction across high-density multiplayer streams. When packet payloads exceed a defined threshold, typically 256 bytes, the NETI pipeline automatically inserts a lib compression handler, compressing raw chunk data and block update arrays on the fly. Furthermore, packets are encrypted using AES CFB 8 symmetric stream ciphers during multiplayer authentication handshakes, securing player session tokens and preventing packet tampering across untrusted internet networks. Having deconstructed JVM performance tuning, region storage, background processing, and network delta protocols, we can now analyze the ultimate architectural paradigm shift in voxel software engineering: the complete rewrite of the voxel engine into C++, known as the Bedrock engine architecture. While Java enabled rapid prototyping and cross-platform adoption during early development iterations, scaling a high-performance voxel engine across resource-constrained hardware, such as mobile smartphones, tablet computers, virtual reality headsets, and home video game consoles, exposed insurmountable JVM runtime limitations. Mobile operating systems enforce tight RAM limits and aggressive power consumption profiles. Running a heavy Java virtual machine with a just-in-time compiler and dynamic garbage collector on a smartphone battery exhausted system memory within minutes and triggered thermal throttling. Furthermore, console hardware platforms prohibit dynamic JIT compilation due to strict platform security policies. On locked console operating systems, applications are forbidden from allocating executable memory pages at runtime, preventing the JVM from JIT compiling bytecode into native assembly. To deploy voxel engines across the global ecosystem of mobile, console, and desktop devices, software architects executed a complete ground-up rewrite in native C++. The C++ Bedrock engine rewrite achieved complete, deterministic control over memory allocation, hardware thread utilization, and graphics API abstractions. In C++, the engine eliminates JVM garbage collection pauses entirely. Memory for chunks, entity pools, and rendering meshes is managed using custom native memory allocators. To understand native memory optimization, consider how C++ handles chunk data arrays. In Java, allocating a new chunk array involves requesting memory from the virtual machine heap, creating object references, and relying on garbage collection to sweep old arrays. In C++, the engine allocates a contiguous block of native memory called an arena allocator. An arena allocator pre-allocates a continuous multi-megabyte block of physical RAM at engine startup. When the world generator creates a new chunk, it carves out a slice of memory directly from the arena buffer by simply incrementing an internal memory offset pointer. When chunks are unloaded, the engine resets the arena pointer or returns the memory to a fixed-size pool allocator. Allocation and deallocation occur in a single CPU instruction cycle, with zero heap fragmentation and zero garbage collection overhead. Furthermore, native C++ compilation allows direct access to CPU hardware SIMD instructions, single instruction, multiple data, such as SSE, AVX, and ARM Neon instruction sets. SIMD vector registers allow a CPU core to perform identical mathematical operations on multiple data values simultaneously in a single clock cycle, like processing 4 or 8 coordinate vectors in a single instruction. In procedural terrain generation and vector matrix transformation, SIMD vectorization yields exponential performance gains. When sampling 3D simplex noise density fields, a standard CPU loop calculates noise for one spatial coordinate at a time. Using SIMD vector instructions, the C++ engine loads 4 or 8 floating point coordinates into a single 128-bit or 256-bit vector register, evaluating noise dot products across 8 spatial points simultaneously. SIMD acceleration accelerates terrain generation and lighting updates by several 100%, allowing mobile devices to render vast landscapes effortlessly. Multi-core hardware utilization in the C++ Bedrock architecture is orchestrated through lock-free task graph job systems. A job system breaks engine workloads into atomic tasks called jobs, using worker threads and lock-free work-stealing queues to distribute work evenly across all CPU cores. In early single-threaded engine iterations, game logic, noise generation, rendering mesh building, and file I/O executed sequentially on a single thread. Modern multi-core processors feature 8, 16, or 32 hardware CPU cores. To saturate all available CPU cores, the C++ engine breaks world workloads into discrete, atomic units of work called jobs. A job system maintains a pool of worker threads, typically one worker thread per logical CPU core, paired with lock-free double-ended work-stealing queues. When the engine needs to generate 20 new chunks, it packages each chunk generation phase into an independent job object and pushes them onto the global job queue. Worker threads continuously pull jobs from the queue and execute them in parallel. If worker thread A finishes its assigned jobs while worker thread B is still processing a heavy lighting queue, worker thread A automatically steals jobs from the back of worker thread B's queue. Lock-free atomic synchronization ensures that threads steal jobs without blocking each other on mutex locks. The task graph job system scales linearly across multi-core processors, ensuring that an 8-core CPU executes world simulation nearly 8 times faster than a single-core processor. Expanding beyond traditional game rendering and cross-platform native compilation, voxel engines have evolved into the premier research environment for embodied artificial intelligence and reinforcement learning. A procedurally generated, three-dimensional voxel world represents a perfect sandbox for training AI agents. Unlike simple two-dimensional arcade games or board games, a voxel universe presents agents with high-dimensional visual input, continuous spatial navigation, sparse reward structures, long-horizon task dependencies, and complex environmental interaction mechanics. An artificial intelligence agent operating in a voxel world must learn to visually navigate terrain, gather raw resources, forge tools, construct complex shelter geometry, and survive against hostile environmental forces. Connecting a high-performance Java or C++ game simulation engine to modern Python-based machine learning frameworks, such as PyTorch or TensorFlow, requires building robust inter-process communication, or IPC, bridge wrappers. In machine learning research, neural network training loops execute inside Python environments to leverage deep learning libraries and GPU tensor accelerators like CUDA. However, the voxel game world simulation runs inside a dedicated Java virtual machine or C++ native engine process. Establishing high-throughput communication between these two environments requires solving severe inter-process latency and data serialization bottlenecks. If an AI agent requests a world observation frame over a slow network interface on every step, inter-process latency stalls the neural network GPU batching pipeline, dropping training throughput to a crawl. Software architects resolve this inter-process bottleneck by implementing low-latency IPC bridges using shared memory-mapped buffers, socket protocols, and gRPC binary wrappers. In a shared memory IPC architecture, such as the MineRL or Voyager frameworks, the game engine process and the Python training process map a shared region of virtual memory directly into their respective process address spaces using operating system primitives like POSIX shared memory or Windows named shared memory. When the game engine ticks, it writes raw visual frame buffers, local 3D voxel tensor matrices, entity vectors, and player inventory states directly into the shared memory buffer. The Python process reads the tensor data directly from physical RAM without incurring serialization overhead or socket copy latency. Zero-copy shared memory access allows reinforcement learning loops to process thousands of environment steps per second, saturating multi-GPU training clusters. To interface seamlessly with standard artificial intelligence research workflows, the IPC wrapper exposes the game engine through standard OpenAI Gym or Ferma Gymnasium environment API abstractions. The wrapper presents the voxel world as a Markov decision process defined by 4 core components: reset, step, observation space, and action space. The observation space translates raw internal game engine state into structured tensor arrays for neural network consumption. A typical observation payload includes 4 distinct modal channels: a high-resolution visual observation tensor containing raw RGB pixel matrices rendered from the agent's first-person camera perspective, a spatial voxel observation tensor containing a localized 3-dimensional integer grid of block IDs surrounding the agent, a status vector containing numeric floats for health, hunger, oxygen, and orientation vectors, and an inventory vector recording item IDs and quantity counts across inventory slots. The action space translates neural network tensor outputs back into executable game engine commands. Action spaces are configured as either discrete key bit masks or continuous vector control channels. In a discrete action space, the neural network outputs integer choices corresponding to movement keys, such as forward, backward, left, right, jump, attack, or place block. In a continuous action space, the network outputs continuous floating point deltas for mouse camera pitch and yaw angles, enabling precise smooth movement control. On every environment step call, the Python agent transmits its action vector across the IPC bridge. The embedded game server thread receives the action packet, injects the inputs into the player entity controller, ticks the world simulation forward by 1 or more steps, evaluates reward functions, such as distance traveled, damage dealt, or diamonds mined, and streams the updated observation state and reward float back to Python. Beyond classical reinforcement learning models like deep Q networks or proximal policy optimization, modern artificial intelligence research utilizes multimodal large language model, or LLM embodied agents, exemplified by architectures like Voyager. LLM agents do not rely solely on raw pixel gradient optimization. Instead, they operate as high-level cognitive orchestrators using code generation and vector database skill libraries. In an LLM-driven embodied agent framework, a large language model is connected to the voxel engine via a Python IPC script wrapper. The LLM receives environmental observations formatted as structured text prompts, describing surrounding biomes, nearby entities, inventory contents, and active health levels. When presented with a high-level goal, such as Mine Diamond or the LLM agent does not output low-level keystroke actions directly. Instead, it engages in hierarchical task planning and code generation. The LLM breaks the high-level goal into intermediate subgoals. First, craft a wooden pickaxe. Second, mine stone. Third, craft a stone pickaxe. Fourth, mine iron, or fifth, smelt iron ingots. Sixth, craft an iron pickaxe. Seventh, explore deep cave coordinates to locate diamond organ. For each subgoal, the LLM agent dynamically generates executable JavaScript or Python code scripts that invoke low-level navigation and block interaction primitives exposed by the IPC wrapper. If a generated code script fails due to an environmental obstacle, such as an entity path block or missing crafting table, the IPC wrapper captures the execution stack trace and streams the error back to the LLM. The language model analyzes the execution error, updates its prompt context, self-corrects the code, and re-executes the script in real time. Furthermore, LLM agents maintain persistent skill libraries stored inside vector databases like Chroma or FAISS. When an agent successfully solves a complex challenge, such as building a furnace or navigating a subterranean cavern, it packages the successful code script into a modular skill function. The agent computes an embedding vector for the skill using an embedding model and indexes the code in its vector database. When presented with new tasks in future exploration sessions, the agent queries its vector database using semantic similarity search, retrieves relevant tested skill functions, and composes complex hierarchical behaviors instantly. This combination of voxel engine spatial discretization, zero-copy IPC memory sharing, dynamic code generation, and vector skill indexing enables AI agents to demonstrate lifelong learning and autonomous mastery across infinite procedural worlds. The evolution from single-threaded Java prototypes to C++ native engines and Python machine learning wrappers illustrates the power of polyglot software architecture. In modern software engineering, dogmatic adherence to a single programming language across an entire enterprise stack is a major design anti-pattern. Professional systems architects evaluate languages based on domain requirements, performance profiles, memory paradigms, and development velocity, assigning specific languages to the specific layers where they excel. In a polyglot voxel engine architecture, software systems are divided into three distinct operational layers: the system's core layer, the application logic layer, and the analytics and intelligence layer. The system's core layer, encompassing low-level graphics rendering, SIMD vector math, memory allocation arenas, and lock-free thread job systems, is authored in compiled native languages like C, C++, or Rust. This layer requires direct hardware control, zero garbage collection overhead, deterministic memory layouts, and inline access to platform-specific graphics APIs like Vulkan, DirectX 12, Metal, and OpenGL-ES. Operating at the bare metal hardware level ensures maximum throughput and minimum frame latencies. The application logic layer, encompassing high-level game mechanics, world entity behaviors, user interface screens, network packet handlers, and modding API extensions, is authored in managed, garbage-collected, or scripted languages like Java, C#, Lua, or WebAssembly. This layer prioritizes memory safety, fast developer iteration, cross-platform sandbox isolation, and dynamic class loading. Using a managed language for application logic prevents third-party community mods or gameplay scripts from executing arbitrary memory corruption attacks or crashing the native engine host. The analytics and intelligence layer, encompassing offline world analysis, procedural terrain validation, automated testing harnesses, and artificial intelligence model training, is authored in dynamic, data-centric languages like Python. Python provides unmatched developer velocity and access to rich scientific computing, data visualization, and machine learning ecosystems. Interfacing these distinct language layers without introducing performance degradation requires clean interlanguage binding interfaces and CABI binary marshalling. CABI, the C Application Binary Interface, acts as the universal lingua franca of computer software. Virtually every major programming language can invoke C-compatible binary function calls. To connect Java application logic to C++ systems core allocators, engineers utilize the Java Native Interface, or JNI, or modern foreign function memory APIs. The engine exposes C++ performance primitives through thin C-style wrapper functions marked with standard export directives. Java loads the native dynamic link library and binds native methods directly to C++ function pointers. To pass large spatial data structures across the JNI boundary without incurring memory copy overhead, the architecture utilizes direct byte buffers. A direct byte buffer allocates native off-heap memory in C++, returning a raw memory address pointer to Java. Java reads and writes primitive integers directly to the native off-heap memory location using unsafe memory accessors, completely bypassing JVM heap garbage collection while allowing C++ rendering pipelines to process the data instantly. Similarly, Python interfaces with C++ or Java libraries using CFFI, types, or PyBind 11 bindings. PyBind 11 compiles C++ classes into native Python extension modules, mapping C++ vectors and matrices directly into NumPy arrays and PyTorch tensors without data duplication. Polyglot software architecture empowers engineering teams to maximize raw hardware performance where memory matters, maximize development speed where feature iteration matters, and harness advanced machine learning research where data intelligence matters. Having deconstructed voxel rendering pipelines, procedural noise generation, spatial bitwise math, region file persistence, background server processing, C++ native task graphs, and inter-process artificial intelligence bridges, we arrive at the definitive software engineering synthesis. The architectural evolution of voxel world engines offers profound, practical takeaways for software engineers, systems architects, and technical leaders building large-scale, high-performance applications across any industry domain. The first fundamental takeaway is the transformation from object-oriented programming, or OOP, paradigms to data-oriented design, or DoD. Traditional object-oriented software engineering teaches developers to encapsulate data and behavior inside domain objects, modeling the world through deep class hierarchies, polymorphic interface inheritance, and object reference graphs. In standard enterprise desktop applications or small web services, object-oriented encapsulation provides clean mental abstractions and fast initial development velocity. However, when scaling high-performance systems that process millions of records per second, whether those records are voxel blocks, financial market trades, real-time telemetry events, or network routing packets, traditional object-oriented design fails at the CPU hardware level. Object-oriented hierarchies scatter data randomly across heap memory, hiding memory addresses behind object headers and pointer references. When a CPU core traverses an array of object references, every pointer dereference incurs a cache miss, forcing the processor to stall for hundreds of clock cycles while fetching data from main system memory. Data-oriented design shifts the architectural focus from abstract object models to the physical hardware reality of CPU caches and memory buses. In data-oriented design, software architects design data structures around continuous memory layouts and hardware cache lines, rather than organizing data as an array of structures, where each object contains mixed fields scattered in memory. Data-oriented design reorganizes data as a structure of arrays or continuous primitive arrays. By flattening three-dimensional spatial coordinates into one-dimensional primitive byte arrays, voxel engines achieve near-perfect CPU level 1 and level 2 cache hit ratios. When a processor fetches a single byte from a flattened primitive array, hardware prefetchers automatically load 64 adjacent bytes into the CPU cache line, allowing subsequent spatial loop iterations to execute instantly. Modern systems engineers must adopt data-oriented design whenever building high-throughput pipelines, designing data layouts to match CPU hardware constraints rather than abstract object modeling dogmas. The second fundamental takeaway is the necessity of decoupled loop synchronization and deterministic tick architectures. A common mistake in game engine design and real-time simulation software is coupling logical state updates directly to variable rendering or event processing frame rates. If an application updates internal state on a variable frame interval, software behavior becomes non-deterministic, varying wildly across different hardware environments, processor clock speeds, and system loads. Professional systems architects eliminate non-determinism by enforcing strict separation between logical simulation tick loops and visual rendering loops. By standardizing internal world simulation around a fixed deterministic tick rate, such as 20 Hz, the engine guarantees that physics calculations, entity movements, redstone logic circuits, and environmental state transitions execute predictably across all machines regardless of GPU rendering speeds. To bridge the gap between coarse 20 Hz simulation ticks and smooth, variable rate rendering pipelines executing at 60, 120, or 240 frames per second, the engine applies linear state interpolation using partial tick offsets. The client renderer calculates a fractional tick offset representing elapsed time between consecutive simulation steps, interpolating visual positions across rendered frames without mutating authoritative underlying simulation state. Furthermore, when server tick loops encounter heavy computational spikes, the engine manages tick drift through deterministic catch-up execution loops. If a heavy workload delays a tick beyond its scheduled interval, the simulation loop executes back-to-back catch-up ticks without sleeping until internal tick clocks realign with real-world time. Decoupling simulation logic from presentation layers and enforcing fixed deterministic tick loops is an essential architectural pattern for real-time simulation engines, industrial robotics controllers, and distributed financial transaction systems. The third fundamental takeaway is spatial aggregation and file system ergonomics in storage architecture. When designing persistent storage systems for massive datasets, software engineers frequently fall into the trap of file granular overdecomposition. Storing each atomic entity, user profile, or spatial data block as an independent file on an operating system file system seems conceptually modular, but in production, it causes severe storage performance degradation. Operating system file systems are not optimized for millions of tiny, independent files. Saving thousands of small individual files saturates file system directory indices, consumes entire disk allocation clusters for sub-kilobyte payloads, exhausts operating system inode metadata tables, and forces physical disk heads to execute mechanical seek operations. Voxel software architects resolved this storage crisis by introducing spatial aggregation container formats, exemplified by the region file system. By grouping 1024 individual chunk volumes into a single consolidated binary container file, the engine shrinks file system file counts by 3 orders of magnitude, completely eliminating OS index overhead, file handle locks, and directory search latencies. To manage variable-sized internal records within a single aggregated file without sequential scanning overhead, the region file format incorporates fixed sector allocation tables and offset headers. The engine calculates an internal entry index instantly from spatial coordinates using bitwise math, seeks directly to the target 4 kilobyte sector offset, and reads the compressed payload in a single continuous disk I/O operation. Furthermore, region files pair sector allocation with streaming's libdeflate compression, trading CPU compute cycles for storage bandwidth. Because modern multi-core CPUs operate exponentially faster than physical disk storage buses, spending CPU worker thread cycles to compress raw payloads before writing to disk yields a massive net performance gain. Modern software engineers building databases, logging aggregators, or telemetry storage engines should adopt spatial aggregation containers, fixed sector headers, and streaming payload compression to optimize storage drive throughput. The fourth fundamental takeaway is the utilization of low-level bitwise math in critical hot paths. In high-performance software engineering, executing arithmetic division, modulo operations, or floating-point multiplication inside loops that run billions of times per second creates a major CPU pipeline bottleneck. Division instructions consume significantly more CPU clock cycles than basic addition or bitwise operations. Voxel software architects bypass arithmetic CPU bottlenecks by structuring spatial dimensions around binary powers of 2, specifically 16. Because 16 is 2 to the 4th power, converting global spatial block coordinates into chunk coordinates and local block offsets is achieved instantly using bitwise arithmetic right shifts and bitwise unmasking. An arithmetic right shift by 4 bits, x 4, replaces integer division by 16, extracting the chunk coordinate in a single CPU instruction cycle. A bitwise an operation with 15, x and 15, replaces modulo division by 16, masking out everything except the lowest 4 bits to yield the local block offset within the chunk. Furthermore, converting 3-dimensional spatial coordinates x, y, and z into a single linear offset within a flattened 1-dimensional memory array is calculated instantly using bitwise shift and bitwise OR operators. Local y, bitwise OR-ed with local z shifted left by 4 bits, bitwise OR-ed with local x shifted left by 8 bits, y, z 4, x, a8. Modern systems engineers must analyze performance-critical hot paths for mathematical simplification, leveraging binary powers of 2, bit shifting, and bit masking to bypass CPU arithmetic pipelines. The fifth fundamental takeaway is asynchronous task graph concurrency and copy-on-write state isolation. In modern multi-core computing environments, running heavy workloads sequentially on a single thread wastes massive CPU hardware capacity, while naive multi-threading with coarse mutex locks introduces thread deadlocks, lock contention spikes, and severe context switching overhead. Professional voxel engine architectures achieve linear multi-core hardware scaling through lock-free task graph job systems paired with copy-on-write memory snapshots. Operations such as procedural noise sampling, lighting propagation, vertex buffer mesh generation, and region file serialization are encapsulated into independent job objects and dispatched to worker thread pools. Worker threads execute jobs concurrently across CPU cores using double-ended work-stealing queues. If a worker thread exhausts its assigned tasks, it steals pending jobs from neighboring thread queues using atomic lock-free operations, ensuring total hardware utilization without thread blocking. To execute heavy background disk persistence without pausing active game simulation threads, the engine implements copy-on-write autosaving. When an autosave checkpoint triggers, the main server thread creates an instant pointer-clone snapshot of dirty chunk arrays in a fraction of a microsecond, clears the dirty flag on active memory, and offloads the cloned snapshot to background I/O worker threads. Active game ticks continue mutating live memory, while background threads compress and write the isolated snapshot to disk concurrently. Isolating active state using copy-on-write snapshots and orchestrating background processing through lock-free task graphs is the gold standard for high-throughput, low-latency concurrent software systems. The sixth fundamental takeaway is polyglot architecture and domain-specific layering. The long engineering journey from rapid Java prototyping to C++ native Bedrock engines and Python machine learning wrappers demonstrates that no single programming language is optimal for every layer of an enterprise software stack. Superior software architecture decouples systems into specialized operational layers, selecting the optimal language, memory model, and runtime environment for each specific domain. C, C++, or Rust for low-level bare-metal hardware graphics, SIMD vectorization, and custom memory arena allocators, Java, C#, or WebAssembly for application logic, game mechanics, memory-safe modding sandboxes, and network packet handling, and Python for machine learning research, data analytics, automated test, harnesses, and AI agent IPC orchestration. Connecting distinct language layers through universal CABI binary interfaces, zero-copy shared memory buffers, and structured gRPC protocols allows engineering teams to maximize raw hardware performance where memory matters, maximize developer velocity where features matter, and harness machine learning intelligence where data matters. Beyond language selection, modern systems engineers must cultivate a deep appreciation for non-blocking hardware I/O and continuous performance profiling. High-throughput software systems cannot rely on naive assumption or intuition. Performance bottlenecks must be identified through empirical CPU profiling, flame graphs, hardware performance countermetrics, and memory bandwidth tracing. When software architects design systems with cache-line ergonomics, lock-free work queues, spatial indices, and zero-copy memory buffers, application throughput increases by orders of magnitude without requiring faster CPU hardware. By applying these core architectural principles, data-oriented design, deterministic tick loops, spatial container aggregation, bitwise math hot paths, copy-on-write task graph concurrency, and domain-layered polyglot architecture, systems engineers can design, build, and scale resilient, high-performance software systems capable of processing vast data volumes across any modern hardware platform. Ultimately, the story of voxel world engineering is a masterclass in software craftsmanship under extreme hardware constraints. What began as a simple block-building experiment evolved into one of the most sophisticated distributed spatial databases and real-time graphics engines in computing history. Every optimization we have deconstructed today, from bitwise right-shift coordinate flattening to subchunk palette compression, 3D simplex noise domain warping, region file sector offset headers, BFS light propagation queues, lock-free work-stealing job graphs, and zero-copy shared memory AI IPC wrappers, was forged by engineers who refused to let memory limits or hardware bottlenecks restrict the scope of human imagination. When you step back and look at a vast procedural world spanning millions of blocks, you are not merely looking at pixels on a screen. You are witnessing the harmonious execution of thousands of software design choices working in unison. You are seeing how data locality keeps CPU caches warm, how fixed tick loops keep simulation deterministic, how asynchronous copy-on-write threads keep frame rates smooth while you sleep, and how polyglot software design bridges bare metal C++ graphics with high-level Python AI research. As software systems engineers, architects, and developers, our primary mission is to approach complex problems with this exact engineering mindset. We must look beyond superficial syntax, challenge dogma, respect underlying hardware physics, and master the trade-offs that govern continuous data flow. By understanding how the systems beneath our code function, we gain the power to build software that is fast, resilient, scalable, and truly timeless.